All right. Hello, everyone, and welcome to our tutorial. Thank you so much for being here today. Our tutorial is Bridging Linguistic Theory and AI, Usage-Based Learning in Humans and Machines. All right, so here you can see the schedule for our tutorial today. We'll start with some introductions to both ourselves and the topics that we'll be covering today in our 4 parts of the tutorial. I'll start by introducing myself. I am Dr. Claire Boniel from U.S. Army Research Lab. I received my PhD in linguistics and cognitive science in 2014 from the University of Colorado Boulder under the guidance of Dr. Martha Palmer. I joined Army Research Lab, which is just outside of Washington, D.C. in 2015, and my current focus areas are in syntax and semantics from a construction grammar perspective. And I bring this theoretical lens to my applied work in situated human-robot dialogue. I'm also adjunct faculty at Georgetown University, where I teach construction grammar and dialogue systems. Okay, now I'll turn it over to our other speakers, starting with Harish.
Thanks, Claire. Hi, I'm Dr. Harish Tayad Madabushi, and I'm a lecturer in artificial intelligence at the University of Bath. And my focus has been in trying to understand reasoning in large language models, in general, and of late in language models, in large language models. I did my PhD in automated question answering at the University of Birmingham, also in the UK. And now I kind of try to explore this idea of how we can build more interesting and explicit reasoning in language models that is a combination of what happens in linguistics and the pure scaling laws associated with language models and so on. Yeah.
Hi, everyone. My name is Dr. Nikhil Krishnaswamy. I'm an assistant professor of computer science at Colorado State University. I received my PhD in 2017 from Brandeis University under the guidance of Dr. James Pustiowski. For the purposes of this tutorial, I studied language by building systems that interact with humans and studying how humans interact with those systems, and also looking at the mathematical and geometric properties of large language models and seeing how those properties align with what we observe in people, or in the cases that they fail to, and I'll be covering both of those topics in this tutorial.
Hi, everyone. Finally, I'm James Pustiowski, professor at Brandeis University in computer science. And I'm the senior member here. I got my PhD in linguistics from UMass Amherst, theoretical linguistics, and I did a postdoc in NLP at UMass Amherst. And I've been at Brandeis teaching and chair of the CL and linguistics programs there for many years. My interest, besides in kind of lexical semantics, computational semantics, temporal and spatial issues of reasoning, I've been interested in the last 10 years in multimodal communication, the establishment of common ground, epistemic reasoning, and also how that can be modeled in vector space, holographic, and hyperbolic vector space representations.
Thank you. You bring the microphone back way down from James. Okay. So we will also have a coffee break before the second half of our tutorial, and we plan to leave time for questions and discussion at the end. Regarding questions and discussion, you can stop us if you'd like to ask us clarification questions, please, during our tutorial. And then for each part of the tutorial, we plan to leave about 5 minutes at the end for questions and more discussion. And then we will have a 30-minute question period at the very end of the tutorial. We have that linked on our website if you are already opened to the website. And then you can also use this QR code to find the question site. So for those dedicated question periods, we'll be using questions from this document. So we encourage you to post your questions or topics that you'd like to talk about. Okay, do we need another moment with the QR code? Okay. Anyone else need another moment for the QR code? Okay. All right, so let's jump into part 1, usage-based language acquisition. So as I mentioned a moment ago in my introduction, my research is primarily focused on human-robot dialogue. So I work at the intersection of NLP and robotics. And in that space, like so many others that are any relation to NLP at all, we've seen a lot of interest in the potential of large language models, as well as vision and language models that share this transformer architecture. And the promise of LLMs in this space, I think, is truly exciting because they can serve as interfaces between people, who of course speak some natural language, and robots, whose limited behaviors have traditionally been dictated in an AI planning language, such as the planning domain definition language. You can see a small snippet of it right here for an opening behavior. So LLMs can serve as in various ways as interfaces to those traditional planners, or as independent planners themselves, directly translating from natural language to an established planning language, or even directly translating code for moving the robot's motors. In a recent survey paper that I've listed here on the planning abilities of large language models, where the authors find, incidentally, that quite bad at planning as independent planners, the authors state, one question that is still not settled is whether transformers learn interpretable causal world models or mostly get by with pattern finding abilities. I think this question has been echoed in a lot of recent research in NLP that looks critically at what LLMs are doing and what they're capable of. Additionally, I'd like to point out that the contrast that's set up here seems to suggest that learning interpretable causal world models would be superior, and perhaps there's the implicit suggestion that that's more like what people do. I actually want to flip this assumption around a bit and ask you to consider, what if you also mostly get by with your pattern finding abilities? This would actually be quite compatible with a usage-based view of language. To explore this question, I'll start by considering what those patterns of language might be that you get by with. I'm taking the theoretical viewpoint of construction grammar, a usage-based grammatical theory. So I will propose that these patterns are constructions, and I'm going to give you a quick crash course into construction grammar. Then I'm going to dive into the construction grammar view of how you learn the patterns of language, giving you the usage-based perspective on language acquisition. Throughout this discussion, I'm going to suggest ways in which this might be similar to or different from what LLMs are doing. And I will close with some thoughts on the implications of those differences and the way and some possibilities to bridge those differences, which will segue us into the other portions of the tutorial. Okay, so we're going to start with our construction grammar crash course. I'm not going to ask you to diagram any sentences because that would be extremely unconstruction grammarian. Instead, I'm just going to ask you to watch a short video, and as you watch, consider how you would describe in language what happens. Okay. So, how would you describe what happened? Does anyone want to volunteer their natural language description of that event? We have some very quiet people. Anyone? Okay, I'll give you some possibilities. She sneezed her coffee? Onto her windscreen? Okay. Melissa, you have any ideas? Mm-hmm. Okay, perfect. Okay, so besides the windscreen part, which that is not what Americans say, but all right. So yes, we have different possibilities of how we could say it. We could say more like Melissa, a woman sneezes and her sneeze blows the foam off of her cappuccino, or we have the more compact version, a bit more like Harish's. She sneezes the foam off of her cappuccino. I actually am thinking that you probably wouldn't say, if you're a native English speaker, she sneezes foam. Because that for me invokes a kind of gross image of her sneeze actually producing foam. So the question is why? Why do the first two, which are actually fairly different in the number of words chosen, in the complexity, seem to convey the same kind of thing, but the last one, which is very similar to number two, conveys something different? And in general, how do we account for the meaning tied to these words? So for some of you, these may be very familiar questions with familiar answers coming from a generative theoretical approach. In the generative theoretical approach, we assume that there are two components involved here. First, you have the lexicon, which are stored word meanings. And second, your knowledge of syntax or the rules of the language, which determine how you put those different pieces together. Under this approach, the verb assigns semantic roles to its constituents. For example, sneeze is going to assign the sneezer role to its subject and the thing sneezed role to its object. But that doesn't seem quite right. We just said that she's not actually sneezing the foam, right? And it's also not clear why under this approach, how we could assign meaning to the prepositional phrase off of her cappuccino. Why would sneeze license that? Because we'll be considering how people learn language today, I also want to note that within this approach, Chomsky and Pinker posit that while people have to learn and store the lexicon of their language, they are born with a pre-existing language faculty that gives them the rules. This is sometimes called an innate grammar or a universal grammar. So they only need a small amount of input in order to map that input onto those pre-existing rules. All right, so let's shift and talk about a construction grammar approach here. Within a construction grammar approach, there's just one set of stored meanings of morphemes, words, and phrases. This is sometimes called a constructicon to contrast it to a lexicon, which would traditionally only include words. One phrasal construction is the caused motion construction, which involves an agent mover, a thing moved, and a path of motion. Instead of the verb assigning these semantic roles, we assume that the construction carries the meanings of these words, which allows us to account for why speakers can readily interpret the meaning of very different verbs within the same template, including she sneezed the foam off the cappuccino, he shook the apple out of the tree, and they talked him into a corner. Now, not many people know this, but construction grammar actually arose organically from the language of construction workers. I'm just going to let that sink in for a moment. Okay, no, I'm kidding. All right. So where did construction come from? Construction grammar come from? It's a usage-based theory of how all people, not just construction workers, develop a grammar of their language, ascribe meaning to certain forms, and generate understandable utterances. Although there are a few different schools or flavors of construction grammar, the agreed upon hallmark of these flavors is that constructions are the basic unit of language as well as the underlying mental grammar. Constructions are defined as pairings of form and meaning. So you can see here on the right, a visual representation of a construction where the form side up top is apple, giving its phonetic detail. So it's given here an IPA transcription. And the meaning side is just a shorthand for the concept of this fruit, apple. So in this sense, the construction is very similar to the Saussurean sign, if you're familiar with that. However, where construction grammar is unique from other theories is that the form side can reflect units of various sizes in language, so not just single words like apple. So we have morphological constructions like the unadjective construction with instantiations like unfair and unreal. We have lexical constructions, including apple, also verbs like go and eat, prepositions like under. And there are also phrasal constructions, which can inherit and combine multiple words or lexical constructions. These include, for example, the transitive construction, I kicked the ball, and the ditransitive, mom poured me more milk. So now that you have some sense of construction grammar, I'll return to our motivating question. What if you also mostly get by with pattern finding abilities? Then how might you learn those patterns of language? Construction grammars are usage-based in the sense that the theories assume that children acquire the grammar or the constructions of their language through language use in everyday life. And they do this with the help of general cognitive processes. So unlike the innate grammar view of Chomsky and Pinker that I introduced earlier, construction grammar research proposes that we may not need any language-specific capabilities, as grammar can be acquired through other established and general cognitive abilities. The first of those is pattern finding. Psycholinguistic research has shown that even 3 to 4 month old babies recognize and respond differently to known objects. So if you are a baby living in a house with a cat, then maybe you know cats. And you would look longer than at an unknown object. For example, here, a dog, even though dogs and cats are actually fairly similar. So this provides evidence that even very young babies are forming mental categories of things in the world. And these mental categories are based on shared patterns like the features of cats. A second ability that is critical to acquisition is intention reading. Language is motivated by a communicative need and our predisposition to jointly attend to things in the world that are moving and potentially displaying agency helps us then to guess what that communicative need or intention might be. Intention reading combined with our ability to communicate with symbols allows us to begin to match up these arbitrary linguistic signs with a particular communicative situation. And finally, cross-modal association is critical to bounding and sort of bundling up which cross-modal inputs should be associated with a particular symbol. When we compare this to what large language models might be doing in processing language, I would say that LLMs are also very good at pattern finding like people. And insofar as this is critical for forming a grammar and subsequently interpreting or generating language, I would say that human and LLM acquisition is surprisingly parallel. While there has been some research into LLMs and theory of mind, which James will talk a bit more about, and this research shows that LLMs might be able to guess at canonical intentions in common scenarios. But because large language models, if they are trained only on text, they can't do cross-modal association. So I would argue that LLMs are also unlikely to be able to read intentions in physically situated communicative contexts in the way that a person can, which involves this kind of weighting and calculation over different cross-modal sensory inputs in order to arrive at the underlying intent, which might be different from the surface word forms. So for example, if I ask now if anyone knows where the thermostat is, and if this room were extremely hot, then you might be aware of what my underlying intention is, that I want to change the temperature of the room. So someone might then say, oh, I'll open a door. And that might not seem like an appropriate response to my question about the location of a thermostat, but it is an appropriate response given what my underlying intention is. So construction grammar was developed for modeling adult language, but here I want to go into a bit more detail on the construction grammar view of child language acquisition, because this will help us to better understand these similarities and differences in how an LLM processes text. So children begin to acquire language around 12 to 14 months of age, and acquisition begins with single word expressions of a child's intention, and that single word is specific to a communicative context. Tomasello calls these hollow phrases. For example, a child might learn to say more in order to express the desire to have more milk in their cup. Now recall that constructions are pairings of form and meaning. Remember that we had our apple with the phonetic transcription of apple, and then on the meaning side, we had a picture of the apple and the notation of that concept. So here, for these hollow phrases in particular, the meaning pole, as we call it, the meaning side of the construction, is not just semantic, but also pragmatic and context dependent. So here, more means more milk in my cup now, please, or maybe not the please with kids, but all right. So what I think this means is that when we compare this to a unigram, what kids already know, despite the fact that they can only generate one word, is much richer than a single word alone. Later, around 18 months of age, children begin to acquire more complex utterance-level constructions. What's striking about these is that they retain one constituent of an acquired hollow phrase, and then they begin to replace one slot in that fixed formula with new elements. So the child might have first learned more in the context of milk, so they might learn more milk. And then they're going to replace one slot to give us more ball, and then there might be something more like more go. Tomasello calls these item-based constructions. And soon after, between 18 and 20 months of age, we see the first traces of acquisition of syntactic marking, such as word order and inflectional morphology. There's also generally an increase at this time in the use and variability of those item-based constructions, which are also sometimes referred to as pivot schemas. And these center on that one fixed lexical item or pivot word. In the case of more, a construction that might have started, again, in the context of asking for more milk would then be extended to other contexts where it might mean something more like more time with a particular toy, or more singing, or more volume of the singing, whatever the child wants more of in that particular context. So this template from Thomas Hoffman's construction grammar textbook shows the more X construction that's drawn from Brain's child acquisition research. So on the form side, you have a phonetic transcription of the child's pronunciation of the word more, and then you have this X. This X is a variable that denotes the schematic or changeable slot. So this is our substantive fixed slot, and this is our schematic or changeable slot. So that's what can denote either car or cookie or whatever. Item-based constructions where the fixed item is a verb are called verb island constructions. Children acquire verb island constructions that are centered on verb pivots. And those verbs tend to be the verbs that are very frequently encountered. And these are likely frequently encountered because their meanings involve some of the most basic situations of life. For English, these verbs tend to be go, denoting movement, put, denoting placement, and give, denoting causing someone to receive something. So children extend those prototypical meanings that I just mentioned from these frequent verb pivot constructions to more abstract constructions. And these are eventually known as argument structure constructions. So this enables adult speakers to extend the semantics of prototypical ditransitives, like he gave me the book, to totally novel ditransitives, such as he WhatsApped me the directions. Another important thing to note about these verb island constructions is that they demonstrate the importance of frequency, as well as the cognitive mechanisms that allow children to abstract over those frequent structures to more general templates. In this process, speakers recognize the similarity of words that can fill certain slots, such as the slot before want. So they might notice that the slot before want is often animate entities or named entities. And as they generalize over that, this gives rise to knowledge of parts of speech, such as noun phrases and proper nouns. And this can then constrain what kinds of words can fill slots within more abstract constructions. Now, I'll note that, of course, frequency plays an important role in language models' processing of text as well, as language modeling sets up prior probabilities of a word appearing in a given context. So, putting this all together, a fluent speaker of language acquires a set of constructions. Again, this is sometimes called the constructicon. Usage and frequency determine what is in a speaker's constructicon. At the very lowest level here in red, we have the speaker's very first constructions, and these are fixed or substantive constructions. So they might only know want milk, mommy, eat, but over time, speakers abstract over the slots in a construction to recognize, for example, the kinds of items that can follow want and eat. And then they might in turn notice the distributional similarities of want and eat themselves, therefore giving rise to a fully schematic, no fixed words involved, kind of construction like a verb phrase construction. Now, I'm not claiming that speakers know what a verb phrase is, rather just that they are able to produce and interpret novel verb phrases without knowing that that's what it's called. So I want to ground this one more time in a phrasal argument structure construction. So in this case of give in the ditransitive, a speaker is first going to experience the ditransitive with a highly frequent verb in that construction, such as I gave him a toy. And then speakers will recognize the similarity of other transfer type verbs falling into this same pattern. So we might see we loaned her a bike. But as they're abstracting over the slots of this construction, they can also recognize and interpret verbs that don't carry any lexical semantic information about transfer in them. For example, he poured her a martini. So with their excellent pattern finding abilities and their exposure to tremendous amounts of text, we are asking if LLMs can abstract in a similar fashion. So Harish will begin to give you a more detailed answer to this question in the next part of the tutorial. But first, I want to point out one piece of evidence from this usage-based picture that might warrant skepticism as to whether language models can do this. Returning to our motivating question, what if you mostly get by with pattern finding abilities? Well, from what we've seen thus far, you may indeed be leveraging your pattern finding abilities a great deal. But your pattern finding abilities and the patterns that you are finding are enriched by much more information than text alone. As Bybee puts it, for each linguistic form that you've encountered, you are storing a tremendous amount of information. This information consists of phonetic detail, including redundant and variable features, the lexical items, and the constructions used, the meaning, inferences made from this meaning, and from the particular context, and the properties of the social, physical, and linguistic context. Storing this information with each encounter with a particular construction leads to a complex memory trace that associates a particular form, including its rich phonetic detail, and meaning, including the communicative function at the time, as well as the social and physical context features. So there's a considerable amount of evidence coming out of cognitive and sociolinguistic research to support the notion of these complex memory traces. But I think that some of the most interesting and relatable research comes from speech and the way that people might pronounce things differently in different contexts. So thus far, I've talked largely about the text form of a construction, but now I'm going to shift gears and just remind you that the spoken form is really what we are considering in a usage-based theory. My favorite studies on this particular topic come from Leboeuf, who focused on the pronunciation of R in different New York dialects. So this is a famous New York dialect that tends to drop the pronunciation of R in post-vowel and word final positions. For example, they would drop the pronunciation of the word final R in wada. So water, wada. There we go. I am obviously not from New York, or maybe it's not obvious, but I am not from New York. So I'm going to allow comedians Amy Poehler and Maya Rudolph to give you a sense of this dialect in a Saturday Night Live skit called Bronx Beat, where the actresses portray homemakers from the Bronx, which is one neighborhood in New York City. All right, so hopefully that gives you a sense that the Bronx speakers drop the pronunciation of the R in wada, while the guest Philly speaker pronounces the R, albeit in a very unique Philly pronunciation of the word water. But I think you can also hear her R's strongly in like yard and peppers and things like that. And the reaction of her very clear pronunciation of R's from the Bronx ladies is that she sounds fancy. So the New York dialect is what Leboeuf was focused on in his study, looking at the pronunciation of R in specifically New York department stores. And the department stores varied in socioeconomic status of the clientele. So he went from relatively inexpensive department stores to very high-class expensive stores. And similar to what the Bronx Beat ladies noticed, Leboeuf's studies found that when speakers wanted to sound fancy in the fancy store, they would pronounce the R, producing the high prestige variant of the dialect. From a usage-based perspective, the explanation for this is that clerks in the higher price stores are exposed to the high prestige variant of the dialect, which involves pronouncing that R, and they store this class information with that rhotic variant of the construction. A follow-up study from Leboeuf further demonstrates that New Yorkers of all socioeconomic strata pronounce the R more frequently in more formal settings. So what this means is that speakers are storing both the fancy form, water, and the not fancy form, wada. And with each form, they also store such contextual socioeconomic information with either the rhotic variant or the non-rhotic variant of that construction. And they're able to deploy this form when the current context calls for it. So let's go back to try to answer this question. Yes, you are leveraging pattern finding abilities to acquire and use language. And like a language model, you are highly cued into the frequency of certain constructions. So that's it. LLMs, they're just like us. Okay, not really, not quite. First, because the patterns you are finding are different from LLMs. Ours are rich with cross-modal associations stemming from our embodied cultural experience. Additionally, the way that you are generalizing over and abstracting from frequent constructions to use and understand infrequent novel constructions is likely different as well, but Harish will talk a bit more about that later on. So do these similarities and differences matter? If LLMs arrive at some kind of similar place in language use, then does it matter how they got there? Well, where LLMs are drawing from patterns of text alone to understand the meaning of, for example, apple here, people are drawing from patterns of symbols associated with these complex memory traces. So when it comes to apples, we're thinking of the taste of an apple, the crunch when we bite into it, maybe even the sound of that. As a result, the meaning pull of the construction for us, as opposed to an LLM, might be quite different. This results in differences in understanding the meaning of language. And that does seem pretty important. This implication is summarized in this paper from Jonathan Bisk and others, Experience Grounds Language. Language understanding research is held back by a failure to relate language to the physical world it describes and to the social interactions it facilitates. Now, this paper is several years old, and we've seen even more advances with larger language models and vision models. So it's fair to ask, is this failure true, or maybe is it still true today? And if we acknowledge that this failure is holding back language understanding research, then how would we address this failure? How would we relate language to the physical world and social interactions? The same paper lays out the trajectory of real-world data that our NLP tools have been able to leverage. In the past, our NLP tools relied on hand-curated or annotated corpora, for example, the Penn Tree Bank. And today, our large language models are trained on internet-scale data. So although our models are limited to acquiring grammar from text patterns, it is a lot of text, arguably encoding a great deal of common sense and cultural information. Increasingly, we are also seeing perception information added in the form of multimodal NLP systems, which maybe combine modalities such as audio, video, images, and text. We are also just beginning to see the opportunity for enriching the linguistic experience with embodied information in the robotics and NLP space. But what I see in my own research on human-robot dialogue is that the sensory inputs of a robot, they greatly differ from a person, of course. So figuring out how we would enrich their constructions with cross-modal association in a similar way is going to be quite challenging. Where we don't see so much deployment and data gathering is in physically situated social interactions. We're living in a moment right now where there is really so much information encoded on the internet, and we've unlocked such powerful tools in LLMs that it may seem like this is enough, that pattern finding from text alone is enough. It may seem like the rest of this information might be gleaned from these other kinds of data might be nice to have, but not really critical. But returning to the gap of social interaction that I mentioned, we are seeing AI assistants, which are largely based in LLM technology, deployed in social situations with children and the elderly, particularly as tutors and aides. But I want to point out that we may be deploying these technologies with the expectation that they can engage in social interaction and understand meaning in socially dependent contexts. But there is really nothing giving these models access to language mapped to situated interactions. So in the same way that I would not expect either a robot or a person to be able to drive a bus after watching hours and hours of first-person video of somebody driving a bus, it might be similarly unreasonable to expect our NLP systems to be able to engage in such social interactions without having the multimodal embodied experience critical to these interactions. And this is a very problematic gap because as we have discussed throughout this tutorial thus far, the primary originating function of language, the reason that you were driven to acquire it, is so that you could fulfill some intention in the world. Arguably, no model will understand even written language the way that you and I do without relating language to the physical world and interactions. All right, so coming up in the tutorial, Harish is going to tell us a bit more about whether or not this failure is still true. And James and Nikhil will begin to supply some ways that we might actually relate language to the physical world and interactions. Okay, and I will pause and let Harish get set up while I take questions. Does anyone have questions? Are there any questions in the document? Does anybody have it up? Okay. Crystal clear. Should I give you a pop quiz on construction grammar?
Yes. Okay. See if that works. Yeah, that does work. Okay. That should be good. Oh, oops. Yeah, hi. All good? Is that okay? Yeah, that's the one. Okay, great. So we'll talk about the next section, which is really the intersection of the theory that was introduced by Claire and what it is that language models can and can't do. So to begin with, see if I can get this to work. Yes, it does work. Okay, so does anyone recognize this? Let me get this out of the way. Can anyone, not that big, that's the top of my head, but other than that, anyone know what this is? Any clue at all? It's by Raphael, if that helps. All right, so it's this. So it's this fresco by Raphael. It's called the School of Athens, right? And it's painted on one of the walls in the Vatican. And the thing that struck me about this when I first saw it was this central piece in this, right? And it depicts on the left, it depicts Plato, and on the right is his student Aristotle, right? And Plato, who's intentionally made to look older, is pointing up, because that is where the notion of what Plato considers reality comes from, which is from above. It is defined and provided to us, as it were, right? And on the right is Aristotle, who's pointing to the ground, because Aristotle believed that reality is defined, it's grounded reality. And to me, this is a perfect analogy of where we are in NLP, right? So you have the slightly older theory-driven mechanisms of how we define what language is, and more importantly, what meaning and cognition is. And now you have the new, more data-driven methods, which are focused in on extracting meaning from purely data-driven methods, right? And it is at this intersection that I think something very, very interesting is happening. We need to understand what it is that language models actually can do and what it is that they can't, right? And the consequences are quite significant. So with that in mind, I'm going to kind of focus in. I'm going to begin by talking about what language models can do, because what they can do is quite impressive and it's quite interesting, right? And we must not dismiss what it is that they can do. So I'm going to spend some time talking about what they can do, and that's important. And then I'm going to generalize and talk about the things that they can't do, right? And I think it's at that intersection that very, very interesting bits of research can come out, and that kind of leads into the kind of research that Nikhil and James are going to be working. To begin with, just a quick recap of language models. And I'm sure all of you already know all of this extremely well, but it's worth thinking about. It's worth kind of just looking back at what all this is. So to begin with, traditional machine learning involved just retraining a model from scratch for every new task, right? So you wanted to do sentiment analysis, you collect data associated with it, and you train a model from scratch. This was obviously wasteful because what we were doing was relearning linguistic priors for every individual task. Clearly, that's not the way we do things, right? So the way around this was to first train a model to understand or to extract some priors associated with language and then transfer that over, so transfer learning, over into the specific task that we're interested in, right? So this is the pre-trained fine-tuned paradigm. And the goal of this was to understand these or extract these linguistic priors. So what is this simplistic task that we can use to extract these priors? Well, this is one such task. It's the closed task, which is also called masked language modeling, right? So what you do is you just mask out a word, and the model is required to now predict that word that we masked out. Of course, that's not the only task. In more generative models, which are the decoder-only models, you have this auto-completion-like task, right? Which is where you provide it with the initial part of a sentence, and the model is now required to complete that sentence, as it were. And so how does this work in actually training a model? It's very simple. You provide a sentence, you mask out a particular word in that sentence, and the model now predicts. Here I've just given you two words, but of course the model will select from amongst its entire vocabulary, and we then provide it with feedback. We know what the original token was. We say, yes, that's the correct one. No, that's the wrong one. And the model will now backpropagate, update its weights. And that's pretty much all there is to it, right? And now we just chuck the entirety of the web at it, and that's it. We just get a language model. So what does this give us? That's the real question, right? So what does pre-training give us? It turns out pre-training gives us a lot. And the way we so recall that we were trying to understand what is the linguistic information that we can extract from this pre-training process. And the way this is done is to actually look at these internal representations, that's the weights within the language model. We freeze those weights, so we fix the weights of this pre-trained language model, and then we learn a one-on-one, a simple mapping from these weights within the language model to some labels that we're interested in, right? So this could be part of speech labels or any other linguistic information. Of course, the model is not going to say this is a noun, that's a word that we made up, but there could be a mapping that we learn from the internal weights of a language model, a pre-trained language model, and these interesting linguistic phenomena. And using this, people found that there was a huge amount of linguistic information that was available to language models. There was part of speech, entities, dependencies, and so on. There was also structural information that was available. That's listed out there, constituents, and so on. What's even more interesting is that you can generalize this to a multilingual context. And it turns out that when you cluster things like dependency pairs in English and French, what you get is clusterings that correspond to gold universal dependency labels. This is fascinating, right? This is not something that either multilingual BERT or the probe were trained on. Without explicitly training on any of this, we're able to find patterns that match UD labels. So straight away, there was a huge amount of linguistic information that was encoded within language models, which were trained only on those two tasks that I told you of, right? So just masking a word and predicting that masked word, it turns out, gives us access to a massive amount of linguistic information. Okay, so, and we know that all of this is kind of encoded in these models. What we're now going to look at is the other side of language. So language itself, there's two aspects to it. One is the formal rules that I just spoke of. And there's a secondary element of it, which is what Claire spoke of, which is the intent that is associated with the language we use. the reasoning, the communicative intent, the actual message, what it encodes in terms of world knowledge and so on, right? And that's now the really interesting bit. How much of that do language models capture, and what is it that they can do in communicating that, right? And that's what we're going to actually spend some time thinking about. So just a quick note on terminology, because I've been using these words, pre-trained language model and large language model, kind of interchangeably. When I say pre-trained language model, I'm referring to these models such as BERT and Roberta, which are pre-trained in this mechanism that I described. Large language models are typically pre-trained models, which are similarly pre-trained, which are generative. So they're not encoder-only models like BERT, but they generate outputs much like GPT, and they're large, right? They're typically larger than about 10 billion parameters. There's something that happens at scale which fundamentally changes what a language model is capable of. And I'm going to say a little more about what it is that might be, and I'm going to demonstrate what those capabilities might be and what that actually means. But it's important to kind of notice that there is this distinction to be made. So really, before we get into that, I think it's worth thinking about what we're actually saying. We're saying that when we start with this task, we call this is the mass language modeling task, we somehow go from here to reasoning. And really, the question is, what gives us the audacity to believe this is even possible, right? Why would this even be possible at any level? And it turns out the answer is somewhere encoded in these examples, right? So I'm going to focus in on the second example here, which is the boring / serene landscape took our breath away. Now, I claim that to correctly fill in that blank, you have to have some quote unquote understanding of what taking someone's breath away entails, right? And of what boring is or serene is, right? Does that seem reasonable? Yeah, I know you're not convinced. You're not convinced precisely because this seems like something the model might have seen. There's a huge amount of data out there. It's all over the internet. And you're thinking, come on, Harish, of course it saw that. There's some co-occurrences. It saw all of the web. Of course, this isn't interesting, right? And I think that is the first section of what we're going to focus in on. We're going to look at what is it that LLMs are doing. Are they just, generating the next likely token? Are they just regurgitating from pre-training data? Have they just memorized the entire web? Is that all they're doing? Or are they doing something more? And I will demonstrate that they're doing something more, and then we'll talk about whether that more is actually reasoning. Okay, so let's start with what it is that they can do. And a good place to start with that is this paper on what are called emergent abilities that was first published by a group from Google. So what you see here on the x-axis is scale in terms of flops, which is actually floating point operations, which is a combination of model size, that's the number of parameters, and the amount of training data it's been trained on. And on the y-axis, what you see is performance on various tasks. Now, don't worry about the individual tasks. I'm going to run you through a couple of them in a bit. But what we're seeing here is pretty much across the board, up until a particular scale, the performance is fairly flat, right? So the models perform along the red line, which is the random baseline. So they're pretty much doing what, just randomly picking things. And at some point, without training explicitly on this data, with no training associated with this task, they suddenly are able to do way above the random baseline. This is non-trivial, and this is fascinating, right? And this is something that we must look at. What is happening here that a model can suddenly solve a task that it was previously unable to solve without being trained on that task? And that's important, okay? So what are these tasks looking like, and why does it matter? Well, it matters because you can't see that. So that's a picture of Geoffrey Hinton, who actually won the Nobel for physics this year, and he won the Nobel for his discovery of backpropagation, right? So these were people who kind of know what they're talking about. Yoshua Bengio was the one who invented attention, and what they put forward is this notion that emergent abilities could lead to an existential threat. Because if models are able to, if reasoning is emergent, maybe they're going to plan and strategize against us. And that's a worry that's being put forward by some fairly prominent scientists. And there's been government action across both the US, the UK, the European Union, and much of the world in trying to understand what this means and what we can do about it. And millions have been kind of invested into research into this. So it really matters what this means and whether these models are actually reasoning or whether they're doing something slightly different. Okay, so what are these tasks that I spoke of and what do they hint at what they're doing? Here's an example, right? So this is from a data set called social IQA, where again, initially the performance is at the random baseline. And as we hit a particular scale, the performance takes off, okay? So what is it? Here's an example. Jordan was in charge of taking the food on a camping trip and left all of the food at home. How would Jordan feel afterwards? And we're going to assume that Jordan likes his friends and therefore he doesn't feel great, right? That's probably a reasonable assumption. And it turns out that that is what a language model comes up with. It says, horrible that he let his friends down. And again, you're not impressed. Or if you're impressed, you're going to hide it. But the point is that at this point, you're probably still thinking, you trained on all of the web. There's probably a Jordan somewhere in there or somebody else, and this isn't interesting. So I'm going to run through this next one, which is called logical deduction. And I'm going to actually step through the task because I'm going to demonstrate that it is not memorized, right? So here's the task. So on the shelf, there are 5 books. They're green, red, yellow, black, and blue. And the yellow book is third from the left. So the yellow book goes over there. And there's the red book, which is second from the left. So that goes over there. The blue book is the rightmost. That goes there. And of course, there's a green book that is left of the yellow book. And now the question is, what is the color of the book that is second from the right? And I know that the only color that's left is black. And that is indeed the answer. And you'll see that the random baseline on this is 20% because there are 5 different options. And GPT-3 achieves a score of about 50% on this, which is quite impressive. This isn't a memory-based task. It's not a task I can memorize. I can change the number of things from 5 to 7. Large models still are able to solve this task. I can change this from a book to something else. I can change it from colors to yet something else, and models can still solve it. This is not memory, right? This is definitely more than memory. Something interesting is going on. And if you're still not convinced, I'm going to give you this example that was put forward by Adele Goldberg, and I'm going to read this out. So this is the prompt. This requires a multimodal model. The prompt is, what is your answer, A or B, and why? This is not an illusion. This requires understanding what DAXI represents. And DAXI is something that's just a made-up word, right? So it's not a thing that exists. Represents an example. And generalizing that from color, which is what it is in this example, to something other than color that it represents in the question. Okay? Does anyone want to risk telling me what they think the answer is? No? I can straight away tell you what GPT-4 thinks the answer is, right? You can ignore the first 2 paragraphs, which is a long rant about what this is. But essentially, it says, in the absence of color variation, DAXI could represent the concept of less or fewer, given that lighter colors are also numerically fewer, as it were, right? If we apply this logic, DAXI in the blue squares would set that to a fewer squares, right? And then it says that the answer is the one which is fewer, and therefore it's A. Now, we can argue over whether this is the correct answer or not, right? And that's not the interesting bit. That's uninteresting. What is interesting is that the model was able to come up with this explanation, which is clearly not memorization. It is clearly not like next slide token generation. Something else is definitely going on. Okay, and I think to dismiss that would be kind of a mistake. Okay, but really now the question is this reasoning? And if you can think of reasoning, and this is a definition that's been put forward by Francois Chauvet, if you think of intelligence and reason, I'm not going to use intelligence, but reasoning as skill acquisition efficiency across different tasks, then we're very close to what that might be. Because remember, what do we start with? Mass language model. And what did we end up with? DAXI. That sounds quite impressive, right? That is not uninteresting, just general. This is something is actually going on. But is it reasoning? And that's, I think, the second bit of what we're going to look at. So what did we start with? We started with what is it that language models can do? They do language quite impressively well. They clearly do more than just next token prediction and memorization. But do they reason? That's the really interesting bit. And if not, what do they do? That's the last bit I'll talk about. And the answer to this question is just spoiler no, right? So they don't reason. But why? Why don't they reason? And what is it that is a failure? And I'm going to, through this kind of thread, I'm going to tell you that it might be linked to this notion of grounding. That might be what is missing, right? But what are the problems of what it is? And what's really important here is this isn't just that. So Claire talked about how the theory behind language learning in people doesn't actually add up if you talk about what LLMs can do, right? It seems like there's a gap there. It's not just the theory. It's also what LLMs can and cannot do. And I will show you, I will demonstrate through what LLMs cannot do that yet reasoning isn't probably what's happening in here. Okay, so that's how we put it together. And so the first bit of that is I'm going to talk about a couple of inherent limitations of these language models. And then I'm going to talk about limitations that demonstrate the divergence from human learning, specifically from children, and the kind of generalizations that we are able to perform. Okay, so let's start with this, which is hallucinations. And this is a problem that is inherent to LLMs, including this state-of-the-art, the biggest and the best model that's available out there, right? So I prompted this model and I said, write a short paragraph on memory in LLMs and so on and so forth. It generates a paragraph which says GPT-3. It cites that. That's surprisingly the correct reference to GPT-3. And then it gives me something else on hallucinations in generated text and bias. And that's a made-up paper, right? So the model just straight away made up this entire reference. It doesn't exist. And this is something that I'm sure you've encountered, right? If you use these models for any length of time, they're definitely going to make something up, which is very plausible sounding, but completely inaccurate, right? And the thing is, this is the closest I could find to the real paper about that. It says, and if you really look at what these titles are, you'll see that there is a surprising, you can almost see the model reaching for that statistically likely similarity out there. Something statistically similar is going on there, right? But this is definitely an inherent problem to language models. The second problem is the need for prompt engineering. Okay, so remember, if these models, and we're talking models that are trained on pretty much all of the web, if these massive models trained on all of the web are able to reason, why then must we do this kind of prompt engineering? And what prompt engineering is that minor variations to the prompts will come up with quite dramatic problems in terms of the output, right? And the model will often change its output from yes to no based on something that basically means the same, a prompt that means the same. This doesn't seem like reasoning, like it seems like something else is going on. The other kind of failure is the fact that LLMs, even though they can solve SATs and answer fairly complex questions, they fail on tasks that 9 and 11-year-olds are able to solve. And I'm not going to run through this example because I don't have time to, but I've linked to all of this. It's our slides are all available on the website, so you can download it and you can take a look at this at this paper, which demonstrates that these models fail on what children are able to do. Here's another problem, which I think really draws us closer to the question of the way in which we generalize and the way in which LLMs generalize, right? Typically fail on what are called counterfactuals. And I'll say more about this generalization failure in the next bit as well. But essentially, models are able to kind of infer what's going on in code, including Python and so on. But if we change Python array indexing from, let's say, 0-based indexing, and we change the array from 0 to 1-based indexing starts from 1, this is something that programmers can very quickly adapt to, right? You tell them, okay, so from now on, every array that you use is going to start with 1, right? And programmers will make a couple of mistakes, but GPT-4 just falls off a cliff in terms of its performance, right? And it's quite dramatic in terms of the failure. So this starts to hint at what might be going on within these models. And it's based on this that we ran these host of experiments that were kind of aimed at using insights from theoretical linguistics in terms of what it is that we know about language and the way we generalize to testing if LLMs do the same. Okay, and this is Yeah, okay. So here's what we did. We created this constructional NLI data set, and it's natural language inference data set based on construction, 8 very common constructions that are, that's a lot of the language that we use are instances of. Here are the 2 examples. I'm going to focus on the first, which is a comparative correlative, where you have this comparison, right? It says the more they work, the more I will pay them. And another example is let alone, where you say Beecher's reputation as a preacher, let alone as a man of God, was not universally accepted. Okay, so these are 2 just example constructions, and we had 8 of these, and I'm going to focus in on just the first one. So here's what we did. We created this NLI data set where you have this premise: the more they work, the more I will pay them. The hypothesis is I intend to compensate my workers based on the amount of work they do, which is indeed the relationship is obviously entailment. This is the typical NLI, but based specifically on this comparative correlative. And unsurprisingly, language models do pretty well on this, right? And we start with GPT 3.5 for O, and that's O1. And O1 gets an accuracy of about 90% across the board. That seems quite impressive and pretty good. Okay, so the question then is, can we make this more interesting? And can we test for generalization like we do in human beings? And we do that by creating this reasoning diagnostic. And we do what we do, and there's a host of different diagnostics that we implement. But the one that I'm going to talk about here is this missing information. So here is the more they work, the more I will pay them. They work more in December than they do in September. How much will I pay them in October? Right? And very quickly, you will see that there isn't enough information. Right? You can't answer this because there is no information. And LLMs, however, fail quite dramatically on these diagnostic tasks. And we also tested this with people, so we know people are able to maintain their performance. They drop slightly, but nothing like this, the way in which LLMs fail. And that, by the way, is GPT-01, which is the thinking model that goes away and does something that nobody knows because they haven't told us. And you'll see that the performance drop there is quite significant also. Okay, so that is quite an impressive drop, right? And this is work by Wes, who I can't see, and Melissa, who's sat right there. Okay, so essentially what this tells us is that these LLMs, there's something else that's going on, and they seem to fail catastrophically in ways that we don't quite fail. Like we don't fail in those ways, and something else is going on. So what is going on? And that is pretty much what we're going to look at next, right? So we're going to conclude with providing an explanation for what LLMs do that explains these competing kind of phenomena, right? So we saw that they can do some pretty impressive things, but they fail quite dramatically in certain other cases. So what is an explanation for all of this? Let me see where I am for time. Okay, good. So let's look at what that might be. And a clue to where this might be comes from this early Anthropic paper on mechanistic interpretability, right? And I've taken a quote here from the actual paper, and there are 2 papers that I've listed there, and they're actually worth reading. They're very interesting papers on mechanistic interpretability. And they define something called a circuit, and I'm not going to say too much more about that, except that it's a list of parameters inside a model, but that's not interesting. But they say that the function of the circuit, as it were, is that they look back over a sequence for previous instances of a current token, in this case, let's say A, find that token the last time and see what comes after that token, say B. And then when they next see A, they're going to increase the probability of B turning up. What does that mean? Let me show you again in this example here. So you have here completely, like this is not a sentence, right? So this is completely made up tokens that are thrown together. The tokens are made up, but the sequence is made up. And you say, every time you see the token node, you're going to then generate this next token, which is, again, a made-up thing instruction, right? And this is really something that the models can do. And this is a model that just does this next token prediction. And a model, the ability to do this, let's call it power to do this, increases with scale. As you make it bigger and bigger, models are able to do this better, right? As you train them on more data, they're able to do this better. And what is this, as it were? What is happening here? Well, it turns out that this pattern completion happens at each layer. So let's say this A thing happens at layer 3. What's now happening is that layer 4, 5, and 6, now what I suddenly have is a higher order co-occurrences that I can capture. I can capture something more abstract at a higher layer because I started this layer where given A, it's going to give me B. If I see A again, it's going to give me B again. This pattern completion at a lower level leads to higher order co-occurrences, which are now really interesting. Okay, and what's even more interesting is that now when I replace A and B with statistical co-occurrences of that in terms of what those words co-occur with, now I get something truly powerful. And what we get is called in-context learning. And this is an example of that. So you take a model which has been trained on just this next token prediction, and you give it these examples. You say, it contains no weight. And then you say, that's negative, right? So these are movie reviews and the sentiment associated with it. And then you say, it makes for very good viewing. And then you say, that's positive, okay? And you say, it brings a smile to your face, and then you stop next token prediction by a language model trained only on next token prediction. It's going to say positive. How is it doing this? Well, I told you, the mechanistic interpretability gives us a hint as to how in-context learning works. There's a huge amount of work that's gone into that, and I'll say more about that in a second. What's really interesting about in-context learning is I can flip negative and positive. Out here, I can make contains no width to be positive, very good viewing to be negative, and now the model will take a positive thing and call it negative. And I can go one step further, and I can say, hey, I'm going to call that foo and bar, my labels associated with it, and now it will continue with this foo bar kind of output. What does this mean? Well, this means that a language model, we can use examples in the prompt of a model to, and I'm going to put this loosely, fine-tune the model in context, right? So that's what in-context learning is almost doing. It's almost allowing you to do this one task, which is just fine-tune the model on the fly and allow it to do something for you, okay? There's still a catch, because first of all, these base models trained only on next sentence completion are able to do this. If I don't give it examples and I give it a question, it's just going to generate more questions because that's sentence completion, right? If you've ever used the base model, you know that's how they work. But what's really interesting is I can't actually do anything with this model. I can't interact with it. I can't do anything with it, right? The only way to deal with it is to what's called instruction tune this model. And I'm going to say a little bit about what that instruction tuning is, because that actually has implications to this so-called reasoning debate that we're talking about. So what is instruction tuning? So this is an example of instruction tuning. You have on the left some premise, hypothesis, and target. This is a simple NLI task that we talked about before. And what instruction tuning does is they create these huge list of templates, 15 to 20, associated with each task, where you say, here's the premise, can we infer the following hypothesis, the options. Then you say, read the following, determine if the hypothesis can be inferred from the premise. You give premise, hypothesis, options, and then you fine-tune the model on this, on thousands of examples, on thousands of tasks. Okay, and this is the only way you can get a model to respond the way ChatGPT and so on do. Okay, and this is the process of what's called instruction tuning. Okay, so with that, we kind of move to one kind of hint that provides us with some information on what might be going on in these models. And to do that, we need to first compare what happens on the right there, left there, which is in-context learning, and what happens on the right here, which is instruction fine-tuning, okay? So this looks like this slide is a bit crowded, so hang with me for a second. What we see there is this in-context, right? So you have these examples. Remember, I have premise, hypothesis, answer, premise, hypothesis, answer, and then I ask the answer, and the model is going to answer this for me, right? So that is just typical in-context learning. And on the right, you will see that basically you have the same thing, but I'm going to now have these different wordings for it. And that kind of provides you with a template for what you're going to instruction tune on. So this looks suspicious straight away, right? I mean, to some of us, it looked quite suspicious. It looks like there seems to be some underlying connection between in-context learning and fine-tuning. And it turns out that there is, and we ran well over 1,000 experiments on a range of models from about 100 million parameters all the way up to 175 billion parameters. And the conclusion was that if you want to understand how a model answers this question, which is, is the following movie review positive? It brings a smile to your face. The way to think about it is to think of it as the model being able to transfer this to in-context examples. So it somehow maps it using the instruction tuning that was done. So using all of the instruction tuning data, not using the data, but the fact that it's been instruction tuned allows the model to map this to this explicit kind of process. Now, what do I mean by that? It doesn't actually do that mapping explicitly, but we can think of it as doing this, right? That's one way for us to interpret what the model is actually doing, right? And this straight away explains a whole host of things. So let me say that again, because this is quite central to what it is that we're talking about. And this is one piece that really explains what it is that models are doing. What is it that I'm claiming? I'm saying this in-context learning exists. I'm able to provide examples, and the model will now complete this in this mechanism. And when we prompt a model like so, one way to think about this is this prompt is being mapped to this kind of in-context learning examples. And what does this explain? Straight away, it explains things like hallucination and the need for prompt engineering. Why? Because if your prompt is not explicit enough that it triggers this in-context learning that we've spoken about, then it's going to default to just next most likely output generation. And then that is the scenario in which it will definitely hallucinate. Okay, so let me say that again. If your prompt is not detailed enough and explicit enough to trigger this kind of mapping to exemplars, then what's going to happen is it's going to default to generating the next most likely output token, right? And then it will hallucinate. And also that is exactly why you need prompt engineering. Why we need prompt engineering? Because what that allows us to do is it allows us to construct that mapping explicitly, right? And if it doesn't happen, then we can change the prompt a little bit and it's able to do the mapping slightly better. Basically, what we're doing is making sure our prompt is closer to what that instruction tuning data looks like, because then it allows that mapping to happen more effectively. Okay, so what really do I mean by this? This still seems a bit vague and out there, right? Like, what do I mean by this? And how do we explain this? The fact that these things fail on tasks that 9 to 11-year-olds can solve, they fail on counterfactuals, and they don't generalize the way we do, right? So what is the explanation for that? So there's a second set of work that kind of addresses this, which is to do with starting with what base models are capable of and extending that to what these instruction tune models are, right? And that kind of explains how these language models work and what that really means. So what's actually going on here? There's a huge host of work on what are base models. What is a base model? It's the model that was just trained on this next token prediction, and that's it, right? And you can't really interact with it or chat with it. That's not possible, yeah? And I don't expect you to read all of this. Again, these slides are available. It's all linked and you can look at it. But essentially what they all suggest is that the way a model does this is when you provide some examples, it's going to use priors from pre-training data to complete that task, right? So the pre-training data is really crucial because what's happening is the model is extrapolating from that pre-training data, and it's going to use priors from pre-training data to solve the specific task that's provided to it in these example settings. And the question really is that the same thing that happens when you instruction tune a model, or does it just wake up and become intelligent, right? That's really what we're all talking about. And this is work that actually went up on arXiv like a week ago, and this involved instruction fine-tuning, again, 70 odd models of scales that vary from 100 million parameters all the way up to 70 billion parameters. And what was found here is that there is a strict correlation, there's a statistically significant correlation between what it is that a base model can do, which is in this slightly lighter color that I call lighter color there, what an instruction tune model can do on this. And what you see here along the spokes are a host of different tasks and what you see along the spoke is performance, right? And you can see that they're they're really correlated. But now you're saying, hey, but yeah, I see they're correlated, that's fine. But what's with this gap? Some of them are overlapping, which means the base model, instruction tool models are about the same. And in some cases, there's this, whoa, massive jump. So maybe there's cases where instruction tool model really does way better and, suddenly starts reasoning, right? Well, it turns out there's a really good explanation for it. It turns out that when you instruction tune on a particular task, the model is going to do really well on that task, right? The instruction tuned version is going to do much, much better on it than the base model. This kind of makes sense. And when you don't train on a particular task, especially if it's out of distribution, then the performance is going to be pretty much close to the base model, right? So if you train on, let's say, natural language inference, then on exactly the same distribution of NLI, it's going to do really well. On a slightly different NLI task, it's going to do worse. And on, let's say, sentiment, it's going to do much worse, almost as well as just, the base model. Did that make sense? Right? So that kind of explains how these two things are related. And really what that means is actually quite significant. It means that what these models are doing is extrapolating from pre-training data. So a model, you provide it with a prompt, it's going to extrapolate and get an answer from its pre-training data. So what does that really entail? So here's a language model, and we walk up with a prompt, and I say, hey, I've got some money, and where in London should I buy a house? This is how a language model is going to solve this prompt, okay? So it's based on all of the things I've told you. This is what it means. It's going to, and this is obviously, it's not going to literally do this, but the way to think about it is that it's going to reach into its pre-training data. Obviously, it didn't do this. Inside is just maths and there's just numbers, but it's going to have it's going to extract those priors from its pre-training data. And it's going to extract those specific priors that are relevant to this task. It's going to isolate those priors which are relevant to this task. And it's going to use those priors to say, oh, this is house price data that we're kind of working on, and these are the priors associated with it. And it's going to generate the answer based on it. Okay. And really, we shouldn't expect it to do anything else. This is literally what machine learning does, right? You train a machine learning model on something, and the machine learning model extrapolates based on that. We trained the language model on all of the web, and it just answers based on extrapolating from that. Why it should do anything more is just, there's no evidence for it, right? And we really need very good evidence to even be able to claim that these models do more. So what we're saying is that there is a very easy and straightforward explanation as to how LLMs do all of the things they do. This also explains all of their shortcomings, and therefore we don't really have to reach for reasoning, right? To claim that their reasoning is really, there's no evidence for it. Okay, what do I mean by extrapolation? It's actually worth explicitly stating this because I'm hinging quite dramatically on that, right? So here's obviously linear regression, which all of you have seen before, right? So you have an input 1 and an output 1, that's a data point. Input 2, output 2, that's a data point. Input 4, output 4, data point, right? This is nothing interesting, nothing dramatic. Well, that is just memorization. So if I went up to this model and said, I give you input 1, what is output? And it says 1, it memorized it, uninteresting, right? That's nothing. And of course, what is that? That is extrapolation right there, right? So if I say, hey, the input is 3, what's the answer now? It's going to say 3. That's not memorization. That wasn't in its pre-training data, right? That is extrapolation, which is why if I prompt a model with something and then I go to its pre-training data, wherever that's available, maybe an open model like Bloom or Pythia, for example, and I search through all of the pile, which is what it's trained on, I may not find the information I'm searching for. That doesn't mean that it's reasoning. It means that it's extrapolating from what it has access to, right? And that is the significant difference. So they're not memorizing, they're not just next word, next likely word, token output, but they're also not reasoning. What they are doing is extrapolation, and at web scale, this is quite powerful, right? I mean, if you extrapolate from all of the web, that's quite impressive. And LLMs are quite impressive, but that's still not reasoning, right? And I've shown you why. I've shown you specific failure modes that demonstrate that they are actually not reasoning. Okay, and just in case you've forgotten, here are the specific ones. They fail on tasks that 11 to 9-year-olds. especially counterfactuals. That's a really interesting one, right? And it's also a good way to test these models, come up with counterfactuals and see if they work on what is a counterfactual. One-based indexing, for example, right? Maths in the base 3, for example, the kind of data that's not available online. Okay. And also, why do new models improve? Because the more we test these models and we put out a paper, they're going to fine tune using that data. And tomorrow it's going to solve that because they fine tune using that data. And we know that once you fine tune a model, it can actually solve those tasks. That's still not interesting. Okay. So just after this definition of reasoning, we said, hey, look, we have these next token prediction task. And it turns out based on that, it can do DAXI. And that seems like reasoning. It seems quite impressive. But now it's suspicious, right? Because what do we have? We have the single task, which is you prompt a model, it's going to extrapolate from pre-training data, and it's going to give you an answer. And that's not generalization, right? That isn't the kind of skill acquisition efficiency that Claire was talking about, that children have, and that Nikhil and James are then going to demonstrate is something that you can try and encode using grounding and so on, okay? So, where does all this go? And I think, there's this fear that, well, there's not much to be done in NLP because, we're at the edge of what we can do and LLMs can do pretty much everything, right? And I think the answer is no, actually, we're at the cusp of something quite fascinating because we can now use LLMs to do this slot filling into the structured things like AMR and all of this kind of historical AI mechanisms that are interpretable and where we have guarantees for success built in, right? And we can fill in information from text using LLMs. And one such example is this generative FrameNet, where, you can use LLMs to generate frames, whereas FrameNet, which was the original kind of source for it, is quite limited, right? Okay, so to wrap up, what is it that we're saying? So we're saying that LLMs solve tasks by extrapolating from pre-training data, right? What do they not do? They explicitly do not regurgitate from pre-training data. They're not just memorized something. That's uninteresting, right? And that's not true. They're not just generating the next likely token. That's not true either. But they're definitely also not reasoning, right? And these are all three of these things are true, which is what they are doing, though, is this intermediary, which is extrapolation from pre-training data. And what does that mean? Well, it's exciting because now what we can do is we can build these grounded systems that I talked about, and then we can do all kinds of grounding, the kind that Nikhil and James are going to be talking about in the next section. Okay, so you can download these slides. All of the work that I've talked about from Anthropic and Google and so on is all linked on my slides. And you can also download all of our slides. So do scan that. And also get in touch with us on email and on social media. I will pause for questions, and I know that you're craving your coffee, so I won't hold you for too long. Are there any questions on the document, possibly? Question. Very exciting. Yeah, so let me repeat that question. First of all, thank you. I'm glad you enjoyed the talk. So this is the question, right? So the question is, hey, you said that's memorization, this is extrapolation. What really is reasoning? I don't know. On this image, I don't quite know. But let me give you an example of the kind of reasoning I'm talking about, which isn't extrapolation from pre-training data, right? Take Darwinian, the theory of evolution, for example. That was a step change in the way we thought. Everyone thought X, and here there was Y, right? Of course, Darwin spoke with others around him, and there's probably some conversations. There's also the notion of the Euclidean way in which the planetary motion, right? Even the notion of democracy, for example, everyone was like, oh, the person with the biggest club is going to tell us what to do. And someone in Greece went, maybe let's talk about it, right? These are fundamentally different from everything that happened up to that point. And some of these people were persecuted for their beliefs, and they stuck to that belief. That is not the kind of thing that an LLM will ever do. We know that the longer you negotiate with an LLM, the less sure it's going to be of its position and so on. That's basically what you're doing, is using the prompt to build priors against whatever priors it already had. That's uninteresting. right? So what does it look like here? I don't know. It probably looks like a curve, right? It looks like maybe a whole other problem, the solution to which is a curve. That isn't extrapolating from this or any data, but it's completely new way of doing something. And I'm suspicious that it's not as rare as, Darwin coming up with a theory. I think we do this quite significantly. I think we do it very in our day-to-day lives. I think we do it quite often, right? And I think to see that what all we do in our life is just extrapolate from pre-training data is not quite giving our human ingenuity its due credit, right? That's my belief. I don't know. Maybe we do extrapolate, but there's evidence that there's a break in it. Maybe the priors themselves are different, and maybe that is the problem, right? Maybe the priors that we have constitute all of these different modalities. And the way, like when I want to learn about something and I want to learn about a bottle or something, I poke it, like as a kid, like you twist it and they throw it around or whatever, right? And that's not the way in which LLMs interact with the world. And maybe providing that, and that's again what James and Nikhil are going to talk about, is an interesting way to get them to have that information. Right? So there's two different ways possibly to deal with that. Any other questions? Yes.
I guess seem to be similar to going reverse culture regression.
Ah.
I think you didn't refer to it, and you of course you referred to other papers that have similar ideas. So, do you think there's a difference between what that paper says, or did you not refer to it for a specific reason because it's quite
Yeah, no, you're right. Yeah, no, thank you for pointing out that paper, and that is actually a brilliant paper. And I think when I prepared the talk, I had to throw out a huge number of papers which were extraordinarily relevant, right? And this was unfortunately one of those papers. So it wasn't that I fundamentally disagree with what they're saying, but I think there's a nuanced difference, which is that the focus of that paper, not necessarily what they were saying, was that this underlying autoregression remains in what we see these models capable of. And I think what I'm saying is in sync with that. We're just saying that when we do in-context learning, it's not just autoregression. It's something more than that. But of course, there's going to be a reliance on that pre-training data, which is exactly going back to what they said. They said, hey, look, there's a correlation between the kind of information that's in pre-training data and the kind of things they can solve. And we're saying pretty much the same thing. We're saying that's just extrapolation from pre-training data. It's another way of saying the same thing, right? And this mechanism, this algorithmic mechanism that basically in-context learning provides still allows you to extrapolate from pre-training data as if in machine learning. I don't have to go around, collect some data, collate it, and train a model. I can just decide on what's relevant data and prompt the model to extract that out. And that is extraordinarily powerful, but not easy. Does that answer your question? Yeah, no problem. I think we're closing to coffee. So, I mean, they're actually passed. So are there any other questions? Was there nothing on the document? I think we should definitely. So yeah, thank you very much. And I'm around. So if you have any questions, just come up to me and we'll also see you afterwards. Okay.
Well, we go until 5:30, right? So we have an hour and a half. Yeah. So we'll take 40 minutes. That gives us.
Very poorly, which is my customary.
And,
thought it was the same size blocks.
Oh, yeah.
and,
Okay.
going around camping.
Yeah, 2 to 3:30 and then 4 to 5:30. Yeah.
It's the same size block. You do. It's only, go to 5:30.
I can't do math. Whatever. It should be fine.
So 40 minutes should be.
I think so.
Yeah, oh, okay.
Is there anything that actually?
Yeah.
No,
No, I think I have to 5:30.
it's a break from 5:30 to 7. Yeah, 1 or 2. Probably go ahead and start, right? Okay. Okay. All right, we'll go ahead and get started so we can end on time. So thanks everybody for coming back. I hope you enjoyed the coffee break. So let's get into some experiments in grounding. And so part of this is to kind of give large language models their due and to show where they actually are reproducing things that we observe in human usage patterns. So just to introduce what I'm going to do in this section, we've probably all heard this common critique of language models that they're ungrounded, and it's important to lay out what we mean by that. So in this case, we mean they lack the ability to link an utterance to a communicative intent. And this is one of the definitions that was proposed in the Fender paper from 2020 that we probably know pretty well. But we can see that also a sophisticated language model can certainly generate accurate text about an object without necessarily understanding what that object is. So here is, I asked ChatGPT, what is a coconut? And it gives me, I'm not a coconut expert, but it gives me what I think is a fairly accurate description of what a coconut is. It doesn't need to have even a picture of a coconut. It doesn't ever have to have interacted with a coconut. This is a definition that can be reproduced based on extrapolating from pre-training data. It may be just memorizing something about a coconut, or it might be generating a novel description, but it's still grounded, relatively speaking, in accurate information about coconuts. So when we say grounding in this sense we're talking about, we usually involve recourse to another modality. And so the typical thing that we think about is going to be language plus images, but there are many other modal channels that we may invoke. Now, of course, there's a wealth of research in cross-modal semantic linking and language grounding to images. So it's important to note that multimodal doesn't just mean language and vision, right? When I learn about things. We all learned about objects as children. We learned about them from interacting with them, right? As Harish mentioned, kids throw things around, they experiment with new items. And so we don't just use image as our only non-linguistic modality. There's a bunch of environmental and sensory information that's implicated in learning. So you can see, here's an example that I'll refer to for roughly the first half of this talk. This is a cone that is being stacked on top of a cube. And depending on where I put this object, it's either going to remain stable or it's going to fall off, right? And the cone is an interesting object in that it's got a flat surface and a round surface. And depending on which of those surfaces it lands on, it's going to behave differently. And I can use this information to give me a definition of what a cone is based solely on its behavior. I may never have heard the word cone, but I can identify this object by the way that it behaves under interaction. So what we're going to do for grounding, I'm going to talk about some stuff that my lab has done, so I can break it down step by step, and then I'll also talk about work that's done with other groups that are similar. In this case, we can use a virtual environment to create experiences for an agent that interacts with the object. And as the object moves, it's going to leave trajectories in space. Then those trajectories are based on the geometric properties of the object and also the affordances. So that is to say, a cone affords being stacked when it's in a particular configuration, and it does not when it's in a different configuration. And so this provides an alternate modal space that is not purely visual that we can use to ground language model representations to. And grounding of concrete terms, as we will see, provides a scaffold for learning and distinguishing the meaning of other types of terms in context. So you can use concrete meaning to ground more abstract meaning. And we can see in which direction this works and where it doesn't. And we can also explore the properties of different language models vis-a-vis size and other factors and see how they behave in this grounding test. So here's the general environmental setup that we're going to use. The simulated environment, we learn to classify a set of objects via similarity learning. This allows us to create representation space and associated object embeddings. And then we can sample sentences from corpus, see how they are encoded in language models. We'll focus on encoder models for the start, and then we'll move on to generative models later. And then we can look at the embeddings of individual tokens and see how those correlate or fail to correlate with the object embeddings and related concepts. And then we can frame this as a regression or a classification task, and we show how the two tasks capitulate similar information. So let's just motivate the psychology behind this. So if you go into the dev psych literature, we can see that as humans are mapping conceptual representations to nouns, they're learning to also segment them from the perceptual flow, and they do this based on experienced interaction. So here's a picture of my daughter playing with blocks, and when she was learning to talk, she was also learning to interact with objects and how to stack and roll and build structures out of Legos. And so at the same time, like she could have learned, what an internal representation of these types of objects are, and learned a term for them that may or may not correlate with, the word block or whatever the equivalent term is in a different language. Now, there's some work from Deidre Gentner that builds on variability in verbal semantics on autonomy. And in this, she argues that the nouns typically learn before a verb, and this can be explained by the variability in verbal semantics. And so we can test this within an embodied simulation, where we use the hypothesis that humans are going to ground the language by activating sensory motor and other situational experiences. That is, we are in a sense extrapolating from our training data, but that training data is of a very different flavor than language training data. That is, I'm going to learn to make predictions about how an object moves based on my previous experience with that and similar objects. And that's also quite powerful, even though it's doing it in a way that is fairly orthogonal to language. Now, we have a problem when we look at the vectors of these different types of models that you're going to train over. If we have a neural language model and let's say an object model, maybe it's based on visual or numerical data, these representation spaces are not directly comparable due to various factors of training data size and training regime. You end up with vectors that are mostly non-overlapping and mostly orthogonal to each other. So we can actually use a grounding function to try and map these representations to each other. And we're going to use a very simple one. It's just an affine transformation, and we'll see that even this very simple transformation is rather remarkably effective. So just watch this little GIF for a little bit. Here are 6 types of objects being stacked on top of a cube, and you can see they all behave quite differently, right? Some of them remain fairly stable, like the cube or this pyramid. Some of them depend on which orientation they're placed in, right? The cylinder or the cone. Some of them are fairly difficult to stack in any orientation, the sphere or the capsule, right? And so you can see that although these objects are distinct, some of them behave in ways that are more similar to each other than they are to others. And we use this information to make inferences about the object behaviors under interaction and use that as a type of classifier. We can do this through similarity learning. What we're going to do is we're just going to gather samples from an agent stacking objects in a virtual environment like so. And the interaction in this case is stacking because it allows us to segment out these kind of flatness versus roundness dependent properties pretty nicely. And the object behavior is going to be bootstrapped from ontological knowledge about symmetry. That is, given the object symmetry of, say, this cone, where it's got symmetry around the y-axis, that's going to kind of condition how it behaves when it's placed in one orientation versus another. So, for example, if I place it on the round edge, it's more likely to roll. If I place it on the flat side, it's going to stay stable. We capture these through the simulated environment. We have these different object types. You can read them there. And there's a bunch of numerical values, a total of 43 that we captured during each object interaction. Then we use a pair-based multi-similarity learning method to successfully classify these objects into their different types. And it's important to note that these classes were unseen during training, right? So here's all these classes, these are the ones that were trained over. And then using just a simple KNN over the embeddings, we enable the model to classify these unseen objects. We can see that there's non-trivial confusion here, but what's interesting is that sil F refers to cylinder on its flat side, sil R refers to cylinder on its round side, similar with cone. Where there's confusion is between the flat versions of these objects, that is the objects that are placed with the flat side down, and between the round versions of these objects, but never between these classes. And so it appears that the model appears to learn this nice contrast between flatness and roundness. And we can see that when we plot the PCs of the embeddings, we see these really nice separable clusters of flat structures and round structures. So now what do we do with this? Let's see how we can ground this to the environment. Right. So we mentioned that the individual embeddings of the same object type can afford these clusters in high dimensional space. You can think of this as each individual sample provides a unique embedding that are similar to each other, but not identical. So you can kind of think of this as like a tight cone in a high dimensional space. And this is a phenomenon that has been observed in the token representations of contextualized vectors from language models. So for example, think of a sentence, right? The same word in a different context in, say, a birth style encoder model is going to be similar, but not identical. That is, every time I have the same token in a novel sentence, I'm going to get a unique embedding for that token. This is how also we can tease out closeness representations like bank as a financial institution versus bank as the shore of a river. So there's some sort of structure in the embedding space, and it suggests that a mapping that preserves that structure can exist between equivalent regions of that embedding space. So we can think of one type of transformation that would do this, which is an affine transformation that preserves collinearity and parallelism. So let's say that we use this embedding space as kind of our target, right? This is our languageless embedding space. It's a model that's been trained over object motion in space. I now want to see if my model can effectively reify the tokens that are being used to describe these properties to the right regions in this space. So we frame this as a question where if you have an agent and it encounters novel objects, can it learn the words for them by grounding them to the object representation space? So what we do is we generate some sentences that contain a target term to be grounded. So you can think of this as a sort of very rigorous, regimented language learning with a child, maybe, where you're sort of pointing to something and you keep saying, that's a ball, that's a ball, that's a ball, that's round, that's round, that's round. And all at the same time, the child is playing with its environment and observing how these things actually operate. And so what we do is we generate these sentences containing a target term, then you extract token representations for those terms of interest. And so we can just go into, say, the final few hidden layers and extract a unique embedding for that token. And then we compute a ridge regression between these paired embedding vectors. So in other words, given two language models, or sorry, two models, one is one of the language model, one is this object representation model. I take token representations from the language model and object representations from the object model, and that will form subspaces within the overall embedding space. Now the vectors chosen from the respective embedding spaces at minimum will form the spanning set of their respective regions. That is, I have a set of vectors that represent either an object under interaction in different instances or a token in different contexts. And let's say I have 3 vectors. They all point in more or less the same direction. They form some sort of region. I can take another vector that represents, let's say, the same token in a different context, and it will fall within that region, or maybe along the edge, or maybe slightly outside it, but it should not stray too far from where that region exists in high-dimensional space. So we choose vectors to represent similar non-identical instances of each token or object in question. And so the optimal transformation would be one that preserves the structure and transforms new object denoting tokens into the object representation region. So let's resume the process. Having computed this transformation, I now need to test it by generating novel sentences that contain instances of this grounded item. Now, if we do this, these are novel sentences. They should be new vectors. They should be close to, but not identical to things we've seen before. If I've learned to quote ground using the structure preserving transformation, I should be able to take these novel terms and they should fall in the right region of the object embedding space. That is, if I've been able to learn what flat means, new instances of the word flat should fall within the region that I understand now to be flat. Step 5 is just the same as step 2. I extract those token representations of novel sentences. Then I use the pre-computed transformation to map those into the embedding space. So for sentence generation, we just use ChatGPT. Right? We've all done this using ChatGPT to generate new sentences. The good thing about ChatGPT, we discovered that it was actually really hard to generate novel sentences about blocks and cylinders. Turns out we're actually not that creative when it comes to really boring things. So ChatGPT is able to generate sentences that are actually unique. Then we prompt ChatGPT with sentences about objects. So like we were told to write 40 short sentences about how blocks are flat on all sides and can be stacked. So we end up with a small corpus of a total of 440 sentences. And then we looked at the most frequently occurring domain appropriate tokens and used those for our target items to ground. So sometimes we're going to be more explicit about the grounding, and sometimes we're going to be more implicit. That is, I'm going to see what other information I can glean given that my transformation has effectively learned what flat or cone means. So these terms are not just the object terms. They may be flat, they may be properties like flat or round, or stable and unstable. They might be behaviors, stack or roll, stand or fall. And we can look and see what happens to these terms as the objects are themselves grounded. We also want to examine how different language models do this, right? We know that individual language models have different internal representations, different behaviors. So we need to assess whether any consistency we see is simply an artifact of a particular model, or if it seems to hold across multiple models. So in this case, we pulled BERT, Roberta, Albert, and XLM. These are all pretty well-known encoder models. And in each case, we compute the transformation using only the object token vectors and the object behavior vectors. So these properties and behavior terms, these are left out entirely. The model never sees these. So what we do is we now take 5 contextualized embeddings of each target word, pair them with 5 randomly selected representations of the associated object. That is, I have a representation for the word block, and I want to be able to see if just by choosing 5 arbitrary representations of the block object, it can learn this transformation. The transformation, of course, is just a ridge regression. And so then we perform these iterative experiments where we are going to incrementally add new object concepts to improve the transformation. So that is, I perform my transformation using just knowledge of blocks and balls, and then we see what else the model can learn about other associated terms or not. And then, of course, we have to evaluate this. We do this by transforming the word concepts for vectors that are not used in computing this transformation. So these will be those property terms like flat or round or stable and unstable. And then we can frame this as a classification problem just using a nearest neighbor classifier. And then the final step, we want to see how much knowledge can be transferred implicitly versus explicitly. So up until this point, we're doing everything just looking at the object terms using in the transformation. And then finally, we provide this explicit hint where we include 5 embeddings of the novel term and the co-occurring object word. So this is a small sample that shows basically a few shot example of what this new term is to see how that affects the grounding properties of the transformation. So here are some results. So what we see here is we look at and see how the transform tokens start to separate when you add more information. So first thing we see is this transformation is only using the vectors for a cube, a sphere, and an egg. These are things that are all flat or all round. And you can see that the flat is pink and round is black. There's a fairly minimal separation between them, but they're already starting to kind of diverge toward the If I use all the object items, now we see that there's a pretty neat overlap between the flat tokens and the flat object, and the round tokens and the round objects. And then finally, if I perform a little hint where I say, okay, you've learned the separation, now let me tell you which one is flat and which one is round, the overlay between the two regions is quite coherent. Now, we see that the clusters of these abstract concept vocabulary, they will separate when the transformation includes only the object words. But different models behave quite differently. So for example, I'll show you flat and round on the 4 models that we tried. So here's Bert, right? This is without the hinting. This is with hinting. So we can see that they separate, but Bert requires this hint in order to get the tokens to ground to the right region. Here is Roberta. This is kind of interesting in that the separation is quite pronounced. However, the object token, the property tokens are kind of going off into space here until I provide the hint. This is a particularly interesting result in that Albert, which is sort of a small model, does quite well without the hinting. And the providing of a hint doesn't actually improve the classification all that much. And here's XLMs we saw previously, and this is the largest model that we tested in this experiment. And so we can see that separation is quite pronounced. However, with the addition of the hint, it ends up being quite a neat overlap. So the next thing that we look at is how addition of information to the transformation affects the similarity of concept clusters. So this is what we see when we add more objects than a small hint sample. So the first thing we're going to look at is how the clusters separate. So here on the y-axis, we see the mean similarity between the cluster of interest, denoted by the colored line. And then on the x-axis, we see whichever information is being added to the grounding model step by step. And so we can see here that as we're adding more information, right, let's say at this point I'm adding information about flat and round, and that affects the separation of other clusters, right, to more or less extent. And so we can see that as I'm adding object terms, flat curve starts to separate, right? And this is more pronounced in certain other models. Then as I add information about flat and round, I start to see more separation between stack and roll in certain models, and then stable and unstable, and so on and so forth. Then finally, if I add the block and ball, this is going to give me a synonym for cube and sphere. And then as I add this other information, it's starting to understand that there is maybe some correlation between this other term for the object word as well. Now, what's interesting is that we perform the inverse experiment, where we now compute the grounding model, grounding transformation, using the abstract term tokens first. So that is, you start performing the transformation using flat and round, stack and roll, and then only at the very end you add the objects. And what we see here is that, subject to some slight variance in the different models, adding the abstract terms to the grounding transformation is far less helpful for classifying the object terms when they're unseen than the inverse is. So that is, I add flat and round, and stack and roll, and stable and unstable, and stand and fall, and then even block and ball. But it's not doing very well at classifying cube and sphere and the other shapes until I actually give it information about those concrete terms. So grounding the object terms helps distinguish the related actions of the properties, which backs up some of the theory from Gettner. But grounding the abstract terms isn't as helpful in making distinctions between the object terms. So we can also reformulate this as a classification task. So we use just a KNN of k equals 5 after all the object and abstract terms are grounded. And the question here is, do the transform word vectors for the object concept terms cluster with the correct set of objects? So that is, do flat and round, do they cluster with the flat and round clusters respectively? Does stack cluster with flat? Does roll cluster with round? And so these results here, we can see that XLM is the largest model, and it's the best one when you provide the hint. And in fact, it approaches almost perfect accuracy, with the exception of this one property here. And so we can see that the larger training size and embedding size may make it better able to represent multiple word senses. Whereas Albert is the smallest model, which is the best without hinting. And so what that suggests is that as we're adding information to the grounding transformation for the Albert vectors, it's kind of bringing a bunch of things along with it, because the training size and the embedding size is much smaller, so as to compress those contextual representations into a smaller space. And so it suggests that there's more interdependency between individual vectors, whereas XLM with its larger embedding size may be able to produce kind of less entangled representations, as it were. So this allows us to make this hypothesis where the XLM representation is less entangled and more compositional, and the Albert representation maybe has its possible bias between or towards noun and verb and adjective correlation. So that is, the object words of the related terms might already have some overlap in the Albert space, and so when I perform that transformation using the object terms, it's bringing along related property and adjectival terms with it. So grounding concepts to the physical environment without this explicit nudging might be more challenging for larger models than smaller ones, which is kind of an interesting finding in that it's somewhat counterintuitive, because you would expect that a larger model would actually be better. But what's better about the larger model is the fact that it allows you to represent different word senses more independently. So now let's review some work from elsewhere, just to show that I'm not completely blowing smoke here. So there's some really interesting work that has come out from UC San Diego, and most of it is encapsulated in this paper from the CL journal called Do LM Language Models and Humans Ground Similarly. So this is by Cameron Jones. It just came out in the journal recently. And in this, they perform a series of different experiments to examine the extent to which multimodal language model representations will encode implicit sensory motor features. And also they examine for which features or modalities are these activations strongest. So what they do is they present stimuli that consist of a sentence and some image or other media that consist of a match between the sentence and one media example and a mismatch between the other. So for example, the ranger saw the eagle in the nest. You would expect the eagle to be positioned like this. The ranger saw the eagle in the sky. You would expect the eagle to be positioned like this. Similarly, for color, for example, Joanne never took milk in her coffee. You would expect the coffee to be dark. If she always took milk in her coffee, you expect the coffee to be white. So there's a match between one pair and a mismatch between the other pair. And so what they do is they tested a bunch of different language models. So there's ImageBind, VIT, and CLAP to see how sensitive they are to the implied sensory motor properties that are made explicit in media. And what they find is that there's an implied feature match for shape and color, but not size, volume, or orientation. And orientation is really interesting. I'll come back to that in a minute, because that also has motivated another experiment I'll show. And so we can see that for, they just use cosine similarity as their metric, and they found that where the features matched, so just to go back to the previous slide, where you have say the shape of an object that matches the sentence, the features that are implied by the sentence also show up in the multimodal model. They then compared the explicit sentences to implicit sentences and the explicit sentences to the media. And so in this case, they also found an effect, a match effect for shape and color. And in two of the models tested, they found an effect for orientation and volume, but none for size. And so what this shows, if you go back to the previous slide, back up one, here we see an implied feature match for shape, color, but not size, volume, and orientation. Here, the effect size, the effect is somewhat different for the different features. And so depending on how you are extracting these matches, you will see match effects for different types of features, which is rather interesting. It also suggests that how you measure really matters. That is, the measurement that you perform over the different types of features that you're assessing is going to give you somewhat different effects. Finally, the other thing they do is they look at human reaction times. That is, they gather human responses for, select the example again, given the sentence, which of these images do you think it should correspond to? This is kind of a pretty standard implicit bias test, effectively. So that is, if I see the ranger saw the eagle in the nest, I should select this one. I should react faster to this one if it's the image presented, and slower to this one if it's the image that's a mismatch. And interestingly, they were just comparing the model effects to pre-recorded human data, but they found that the language model representations correlate with the human representations. However, the correlation is insufficient to account for the main effect of the matching or mismatching between the sentences in the medium. And they found that the sensory motor features play a stronger role in human reaction time than in the language model representation. And so they kind of end the paper with the supposition that these features are either automatically activated or they're strategically task dependent. And so again, we see some correlations between various measurements of human capacity and various measurements of the language model, but the method of measurement is quite important, and the way that you source your samples is also very important. So the next thing I want to cover is grounding for physical situated reason. So we've explored a bunch of different ways of correlating, object representations and language models, and then we can see how these manifest in large language models. So here's an example of how LLMs do at physical reasoning tasks. I need to get to the top of a platform that is 2 meters high. The highest I can jump is 1 meter. I have 2 cubes that are both 1 meter long on all sides, a sphere that is 1 meter in diameter, and a cylinder with major axis is 1 meter long. How can I get to the top of the platform? Now, if these are the objects that you have, we have 2 cubes, 1, 2, a sphere, and a cylinder. A solution would be to turn the cylinder on its side so that it's standing flat and use that and the 2 cubes to build a staircase. However, this is what ChatGPT tells you when you actually visualize this. This is what you get. ChatGPT is not the only thing that sucks at this, because Llama 2 does the same thing as so does Llama, just they give you different wrong answers. So how do LLMs do at physical reasoning tasks? Bad. But why? Why would we think that LLMs would fail at situational modeling? So these distributional approaches learn usage, but they're less successful learning conventions. And we can motivate this by the property of generative alignment methods. So if we look at reinforcement learning for human feedback or direct preference optimization, generally what we see is that your objective is to fit this reward model by using the reward advantage of a winning sample YW over a losing sample YL for a context X. These are just responses. So let's assume that big Y is the space of all possible outputs. Let's sample 2 distributions, A and B. Each of these represents similar semantics, but they're disjuncts. These are basically similar ways of representing the same thing. And now let's take a particular example, YA that is drawn from A and YB that is drawn from B. In the case where YA is clearly preferred to YB, we see the following. So the log sigmoid of the reward difference goes to 0. And so over a large sample size, the expected value also goes to 0. If this is the ground truth, then the reward model for the sample is close to correct, meaning that the value of the loss is small, and so is the resulting update. However, if the reward model is very wrong, then the expected value of the log sigmoid goes to infinity, resulting in large updates. So over time, the reward model learns to score samples from A higher than samples from B. And now if A wins over B and B consistently wins over another output C, the reward model implicitly learns to score YA higher than YC, even if they never directly compete. But now consider samples where the opposite is true. We actually have samples in the data where YC, this new response, is preferred to YA. This creates this non-deterministic relation between these outputs A, B, and C. So in this case, where you have C is preferred to A, the expected value of this log sigmoid, that also goes to infinity. And so this causes larger updates when it comes to training these samples. Now, depending on the exact proportion of samples where this is the case, we may see 2 possible outcomes where the reward model either underfits to samples where C is preferred to A, or underfits to samples where A is preferred to C. And so these preference scores are made only based on the text context of the outputs. Now, in real-world, real-time settings, we have a bunch of variables that are actually hidden to the language model, and these things change over time. So if you'll excuse me while I just go back, we can see that ChatGPT's response here is stepwise. If I actually execute one of these steps, that changes the context. But the context has not, the context X, that is the prompt, has not changed. And so what we find is that in physical reasoning, these hidden variables would be an externally validatable work model. You can also think of how in human AI dialogue, this might be the human's mental model. It's basically hidden to the language model. They change over time, and as they change, so do the implicit preferences for what the right answer is. This embodied simulation features are implied in event descriptions. So following the findings about orientation, we can see that certain language models will identify object affordances, but habitats, which I'll define in a minute, remain challenging. We can also think about what the social affordances might be created by collaborative dialogue, which James will discuss. So Habitats are these locally scoped environments that contextualize an item and condition its behavior. So for example, the screwdriver needs to be inserted in the head of a screw in order to screw it in. Affordances are typically selected by the matrix verb, such as a screwdriver screwing in a screw. Habitats are typically implicit and therefore still sparse in training data. So last experiment that we did is we collected a data set of affordance and habitat centering questions, and we evaluated a whole bunch of large language models on them. So we can see the linguistic input may not allow an LLM to ground externally as humans do. So we expect that images should disambiguate condition responses. So we collected a bunch of images to go along with these questions and evaluated 16 open weight large language models on this question answering. And how do they do? Well, on affordances, some of them do actually pretty well. That is, given the question, it's able to tell you what the affordance of the object is. Some of them are pretty bad, but at least on the best ones, you're approaching 80%, which is about human performance for a simpler task. But when it comes to habitats, many of which consist of orientation, they're consistently bad. And it's rather striking that there's a plateau of about 60% accuracy, and sometimes the image inputs actually hurt. So these orange ones are the multimodal language models where images were included, and many of them are not any better than the text-only models. So this supports the hypothesis that the LLMs should underperform on habitat reasoning. And so we can see that given the context that's supplied by the habitat, the language model does not really keep track of the change in context that would cause the answer to be different. We see strong biases toward canonical object position. So for example, here we see, chair legs are pointing downward. This is a chair that is upside down. It is clear in this one here. Grounding of the term downward is focused on the upper part of the image where the legs are, because the language model is used to legs being in the down position. So this indicates that where LLMs are learning conventional usage, these conventions form a strong prior, where it's got a strong bias toward what it's seen in the pre-training data, and it's extrapolating towards that, but it's not accounting for the change in the context that prompts a very different answer. And so this environmental context ends up being this hidden variable that's present during alignment and training with the LLM, simply you can't see it. So in conclusion, we can see that sufficiently large data has allowed us to learn patterns of usage that are similar to human usage. These patterns are robust to the extent that we find these pseudo-homeomorphic structures that occur between LLMs and other types of models over different data. The literature also shows some similarity in how humans and LLMs perform grounding. But we also see that they're kind of amusingly non-robust to multi-step physical tasks. And we can motivate why this is based on the properties of common generative alignment methods. In this, we see the environmental context constitutes a variable that is hidden from the language model. And so now we can ask the question, how do we encode this information in a way that allows language technology to use this effectively, particularly when the context is non-deterministic or multi-step? I won't take any questions at this time, otherwise I'll leave it to James. Okay, we have 2 minutes for questions. All right. And go ahead and give the Zoom link.
You need to invite them in there. You just need to sub them.
Thank you for the talk. I have a question about the paper by Jones et al. Do humans and language models ground similarity? Yeah. So for instance, for size, would there be a reference in the picture? For instance, for the beer bottle, would there be only the bottle in the picture, or would there be another object for reference?
I believe in that experiment, it was just the item.
So for language models, if the size is in pixels, how is it supposed to judge if it's large or small?
If the size is in pixels, I believe what they did is they took the entire image. So for the bottle, for example, you'd see, say, a bottle that takes up most of the white space, and then a bottle where there's a lot of white space with a small bottle in there. And so I believe they took the entire image, and unlike with a vision encoder, they didn't do object detection first. They basically take the entire image and feed it in, so they normalize for the size of the background.
I see. So the same probably goes for sound. The sound volume wouldn't be in reference to another sound. It would be just
right. It's basically, I think everything, as far as I understand, everything in the test data set was normalized relative to a baseline.
I see. Thank you.
Hey, check 1, 2, hey.
I don't know.
Hey, sure.
Somebody else's night.
I don't know where that came from.
Yeah, okay.
Oh, yeah.
As I listened to your talk, it felt more deeper than tutorial level material. But
All right. Okay, great.
Okay, so let's pivot to the last section of the tutorial, which is trying to account for some of the components that have not been addressed yet in what capabilities and competencies large language models might have. So story so far, we have a discussion of and an elaboration of construction-based meaning, which offers a strategy for moving beyond text and speech for understanding any nature of language, but specifically here, dialogue I'm going to focus on. Leveraging situational knowledge from LLMs, Harish was talking about, is robust as long as we prompt with the appropriate language in textually trained models. So it's really key that there are reifications in the language that is represented in the model for the type of concept that you're looking at. Hence, as we get to some of the hidden variables that Nikhil was alluding to in the affordance and habitat work, if it's not so readily encoded, either through reification, lexically, or systematically in constructions or syntax, you're going to have a harder time actually recovering that type of information, even from large language models. So the takeaway here is there's a lot of dark matter, and it's not just the issue of getting more and more data. It's a matter of how to do a number of things, and we're going to discuss this with our takeaway questions, which is going to have to do with how to map information from the domain to text or whatever the native language.
Keep going.
Oh,
You need to be sharing your screen.
oh, I'm sorry, I'm sharing screen. Let me do it. That's why it wasn't showing. Got it. Thank you. Okay, so I'm going to discuss situated constructional meaning, and extending from what everyone has said so far, particularly from what Nikhil had been talking about with affordances and other object interactions, namely the notion of situated grounding. I'm going to talk about epistemic situated grounding. What do we know? What do I know that somebody else knows? And what are our intentions in discourse? So the outline will be looking at what the components of multimodal communication are, which is going to be first kind of a characterization of it as a situated constructional meaning. I'll look at the theory of mind, which is going to allow us to explore just what is missing and what is present in LLMs, and then talk about two experiments that we've done with Nikhil's lab and my lab on multimodal interpretation of common ground tracking. So coming back about 10 years ago, DARPA came up with a notion of the hallmarks of education of communication between humans and hence human and machine, or human and robot. Agents need to possess the following capabilities: move the conversation forward, steer the course of the interaction, align generation and understanding. All those are fairly robust with current systems. Able to make appropriate use of multimodal communication, not so great. And then clearly reference items in the interaction based on a frame of reference, depends on the context, and then demonstrate knowledge of the changing situation. Very weak. So we construe that in the context of today's tutorial as constructing meaning in a multimodal communication. We see that one, agents are embodied in the interaction. This is important, not just grounded, but you're embodied. All the actions are affected and interpreted through your embodiment. That's experiential and episodic, both things which LLMs have no clue of. Objects and actions are situated in the interaction. So my view and any other agent in the context behave and act according to object-specific knowledge. That's the habitats and affordances that Nikhil was mentioning. Furthermore, importantly, what I'll focus on today is that the agents establish this common ground through a number of modalities. Our speech, which can be either textually input or our speech acts, gestures, a number of gesture types from pointing to symbols to iconic, metaphoric, and then perception. Perception is all around. Whatever the perception might be, it does not have to be vision. It can be proprioceptive, haptic, auditory. Agents will dynamically update both the epistemic as well as the ontic. Ontic is things that's happening in the world. Epistemic is how I'm reflecting on what you just said, what's happening, what I'm thinking, and what I've just seen happening in the world. But it's important that we look at both ontic and epistemic aspects of common ground. So first, let's talk about what the situated constructional meaning might be in the context of constructions. It's pretty straightforward. We look at the idea of emerging from the integration of language, linguistic forms, and context. That's straight away fairly obvious. But how do they shape constructional meaning in a context? So we know construction grammar from Claire's presentation. The relevance here is that it's going to emphasize data-driven generalizations, aligning with ML paradigms. So I will just define, for the purposes of today's tutorial, situated meaning arising from interactions involve language, physical environment, social context. That's going to be the multimodality of my interactions, the context I'm sharing, and the dynamics of the interaction. So push on it, it's going to be a gesture. I don't need to give you examples. We encounter these every day. The impact is going to be that contextual cues will disambiguate linguistic input, which will enhance our precision. So constructions are going to enrich this context. Examples of enrichment, I have some examples that I can skip over, but I have a ditransitive construction in the linguistic terms. Give her the book with a deixis, gives me a special situated construction, which is the gesture specific to the recipient, and so on and so forth. So I could just take this to be essentially a tuple, the form, the meaning, and the context to give me this sort of situated construction. So usage-based learning for this then is going to be fairly straightforward. I have an example of pattern generalization, contextual grounding, frequency effects, all the things that we're going to see from linguistics and other types of constructional learning. And examples are very easy to come by in all types of scenarios from workplace environments, children, education. So I have various examples of a child contextualized within a learning situation. I can extract a pattern. I have a result of some sort of interaction and utilizing the integration of a deixis plus some underspecified linguistic imperative expression. Collaboration between a robot. Lift this box here. Needs to be, of course, paired with the visuals of what are you looking at? Not just pointing at, but what am I actually gazing at? This is really critical. So I'm extracting a pattern. It's a transitive construction, which might be associated with a particular constructicon item. I have the multimodal context, which was going to be some way of capturing the spatial proximity, my gaze alignment, not somebody else's, and my gesture if I happen to provide it. Grounding is going to be the context of the workspace. That's the embodiment and the embedding space. And the result is hopefully that the robot can take all these in, align them appropriately, and create a type of abstraction, which we'll call a situated construction. Human learning would be the same thing. And in simulations, I'm not going to dwell on this. You can look at the slides in due time. I just want to make sure that we get through all the material here. So let's look at the specific context that we've been doing experiments on, and that is AI in the classroom. So we have middle schoolers doing sensor immersion, STEM type exercises. This is something called the sensor immersion lab. And the thing about these that's really quite interesting is I've got here a dyad, 2 students working to assemble this little unit, which basically measures the sound or the moisture or the temperature of some element in the room. And the interesting about these experiments for our studying to train models, ML models, is it's a natural interaction of multiple modalities. Natural speech, a lot of gesture, attention and co-attention, and then the posture indicates engagement or disengagement generally. So here we just have an annotation. There's a gazing. They're both gazing at an object. That's called a joint attention. They're leaning both in. And that is generally associated, as I mentioned, with being involved. And there's further things that we're going to explore with the annotation of those as in the due course. So our goal here that I want to summarize for you and report on in the context of the overall consequences of usage-based learning in LLMs is the following. I want to focus right now on theory of mind. And the real problem that we have with LLMs is being able to understand the shared belief space held by participants. Even just a user in a chat bot, it's very hard to get the intent. Intent and entity recognition is the hallmarks of chatbots. But the more complex the interaction, the more difficult it is to actually extract a unique intention. And when you have multiple parties in a live dialogue, it's close to a wash. So what this entails is logging the current beliefs and a level of confidence for each of these, but also identifying a mistake, a false belief, or recognizing that someone was looking away while I did something, so they just missed out. And that's also a kind of false belief or lack of information. And then this is actually, we want this to provide a richer snapshot of the dialogue situation, which, as you might imagine, would provide, let's say, information to prompt an LLM if you're doing prompt-based in-context learning, or some other type of recurrent neural net. So DNNs specify the ability to do speech, gesture, gaze, as well as jointly perceived action, that they're all quite robust at this, but they don't give you the epistemic content. They don't give you any information directly about what the belief of the individuals would be. So what we've been building essentially is integrating symbolic techniques with the output, and then the output to neural nets, which is one type of neurosymbolic architecture that we just call neurosymbolic network. They're hybrid systems that integrate pattern recognition from neural net output, but also the symbolic system has explicit representation inside, but it also outputs and perhaps creates an embedding or some type of vector representation that feeds again to another neural net. So it's a pipeline of something that could be neural symbolic, neural symbolic, neural symbolic. The benefits are very high interpretability. It allows for simple or easier multimodal integration, and it also allows for high degree of compositionality in the sense of semantic interpretation. Core aspects, as you might imagine, would be a neural component which processes the raw sense data, so vision, gaze, audio, action. It's going to learn these feature embeddings. The symbolic component can be whatever you want it to be. It's going to be classic modal logic. It could be syntactic representations, semantic representations, anything that you really need for the purpose of your task. And then it's going to have mapping functions between them. So the basic structure in shell is nothing too bold. It's basically going to be this four tuple of the neural networks, symbolic reasoning modules, and then the mappings between them. So now let's get to some of the data. So theory of mind essentially is this cognitive ability to attribute mental states to oneself and also to another. And it's absolutely critical for us for understanding that others have beliefs and desires that are different from one's own. In humans, this is what gives us this ability to socially interact and communicate. So the goal here in multimodal dialogue is that TOM actually is what is the glue or the enabler for people to understand and interpret each other's communications that go beyond just speech. So the rest of this talk is going to be basically called Beyond Speech. In multimodal dialogue, theory of mind allows you to take the verbal cues and integrate them with NVB, nonverbal behavior, nonverbal cues, such as pointing, attention, posture, and shrugs, and whatever it might be. And this integration is critical. This is, in fact, one of the biggest problems, is doing the alignment and integration and making it semantically coherent and informative. So common ground in philosophy, in psychology, and in pragmatics is a well-studied area. I'm not going to go into any of the details, except just give a couple of hallmark accomplishments. It's essentially agreed upon that it's the ability to have a shared context through co-situational and co-perceptual anchors. We need to identify what are those anchors? What is a situation? And we have to also be clear on what is a shared experience. You can witness, you can hear, and you can feel. These are all going to be shared, but in different ways. You have agents that are in shared actions. You can co-intend and you can co-attend without the same intention. So one of the problems we're going to look at is an experimental setup called the Fibonacci weights task. A triad students are working together to figure out the weights of 5 differently colored blocks, and they're going to make comparisons using a scale. And the group deduces the correct block weights, giving a consistent state, determining that it's actually in the Fibonacci series. There are false beliefs in this weight task. I'll just go to okay. No, I'm gonna ignore this. I'll just skip over it. That's okay. Now I'll get to an example of false beliefs in a second. So let's go to one of the mechanisms, one of the toolboxes we're going to use. It's called epistemic logic, as applied to changing situations. It's called dynamic epistemic logic. So it's been around in modal logic for about 15 years, and it's rarely used in the context of bringing a kind of more formal representation to LLMs. There are some exceptions in human robotic interactions, however. So there's a dynamic logic, which basically is going to model the impact of events and actions on agents. There's an event model, which basically tells you what happens after an event is performed. So if I'm going to open a door, it's closed before I perform some action and it's open. Pretty straightforward. And then the update mechanism is, how do I actually change the world, either on the object aspect of the world by changing the actual data structure, values, and then also, how do I change your world, your mind? And that's called a public announcement. I'm telling you something. It's sunny outside, it's rainy outside, and I want you to take into consideration that propositional expression, a speech act, and change your mind. Namely, you didn't know that before. So we're going to use this particular model of belief, which allows us a nuanced set of not necessarily being sure about something. You have evidence for something and you have less evidence for something. It's called evidence-based belief model for dynamic epistemic logic. It's really straightforward. got a lot of formulas in it, but it's actually really quite simple. It gives you a model for taking a proposition and saying, I have evidence for this thing, but I don't know for sure. And basically, it's really quite a simple logic. It's just a tuple of, it's just a kind of a modal logic, where you basically have worlds where propositions are true, and I'm an agent, and I've got accessibility, I've got relationships to all these where I can believe something or I have evidence for something. And so you have worlds and evidence valuation, evidence relations and evaluation function where a proposition is true. We don't need to get into any of the details of this. You can explore this in the slides later if you wish. But the point is that there's information coming in from the environment, and it gives me evidence towards some propositional content. And I want to take that and accumulate it to form beliefs. And then hence, after that, perhaps even knowledge. So it's going to be all the sets of evidence that accumulate so far that I can say goes towards my believing something. Now, if I have evidence that it's raining outside because I see someone wearing a raincoat, but then I have evidence that it's sunny outside because someone's wearing short pants and has sunglasses on, that's okay in an evidence model. You can have contradictory evidence, but you can't have contradictory belief as me, one agent. So eventually, you want to come up with a stronger sense of what a proposition is relative to my epistemic state. And that is to look at all those worlds that are essentially going to be consistent with one another. So I'm going to take the intersection of all of those that have only the appropriate propositions that I'm looking for to be true. Now, one thing that's really important about perception in particular is that there is very rarely a true veridical perception. So I can see something and it looked like a car, and someone else sees something and it can look like a moose or something. And one of the problems with entrusting the vision of self-driving cars is, of course, the problem of non-veridical perception. It's all based on the models that the self-driving vision systems are trained on, and you don't necessarily have a veridical input from the visual flow to your conceptualization of it. It's entirely based on the model. So there's a perceptual or evidential or inferential aspect to the information. So you get the information, you have to infer something by doing some sort of inference. So that's a degree. So given this, we can quickly go through this to say we have degrees of belief. Now, one thing that we're going to see very importantly is something that in the robotics world is very important. They make this general assumption that if you see something, you're going to believe it. So it's called seeing is believing. And so shared belief, without looking at the details of this, is essentially if I have a belief about something and you have a belief about something, we have a common belief. If everyone in the group has that, we have the intersection of those, and that will be the common ground of this group. Okay, now I need to talk very briefly about something called false belief. This is the Sally Ann task, which we're actually doing experiments on currently. This was originally seen as a study of cognitive development in children to see at what stage can I attribute another state of mind to an individual that's not my own. So here's the situation in a cartoon strip. Sally and Ann are in a room. There's a basket and a marble. Sally puts the marble in her basket. She leaves. Ann, a little devil, she moves the marble and moves it into the box. Sally comes back, and the issue is you ask the child, where does she look for the marble? The child's been watching this. So the child at one age will attribute the knowledge that she has watching it to Sally, who went out. At a later stage, usually seen to be more developmentally mature, the child will actually attribute this false belief by virtue of not having the perceptual input. So these have remarkably elegant and really, really concise graphical representations in what's called an event model. And the event model is something that can be encoded with very, very nice holographic representation, which I'm not going to talk about today. You can encode them with vectors. But here's just as a modal system in a graph, basically you have the following. I have my current world, And Sally and Ann both believe that the marble is in the basket. After she has moved it, Anne, we basically, if Sally comes back, we have the real world where Anne knows what's happening. It's now in the box. Sally, however, is actually living in another world. That's the extends to another world, wherein she believes both Sally and Anne think that it's still in the basket. That's a very concise representation of about 25 propositions. So this is an incredible densification of the situation. Now, updating the common ground is essentially what we do every day in every context to move things forward. So I'd say, well, I want to go to get coffee. Well, I want to get tea, or whatever it might be. So you're throwing out there your preference and you're making it public. So the way this is represented as an update, it's kind of like an assignment statement, but you're also adding something to a stack. It's not just assignment by changing a value. You're actually adding to a stack or a queue. So this basically is going to be an agent making an announcement of phi. Now, I say phi. Psi is going to be now known. Psi is going to be, say, I say it's raining, and psi is basically, you need a raincoat. Phi always announces itself, but this is something that it has consequences. So I want to basically relativize this to evidence, though. So I want to say, well, you know, you can say something, but I don't necessarily believe it. So I want to basically hedge a little bit. So you can say phi, and maybe I'll take that to be evidence for phi. So, okay, I'm hedging my bets. Now, we're going to do this when we do our updating of common ground in the experiments. But then if I already got evidence and somebody else comes along, that'll be a different agent, says, you know, phi seems to be true. So basically we're doing the weights task and somebody says, you know, the red block is 10. And so I say, okay, there's evidence that the red block is 10. Somebody else comes along and says, you know, no, the red block is 10. So I'm going to say, okay, I believe it's 10. So basically that's one way of doing it. So I'm going to update, say it's 10. So now let's go to the experiment and the design. We have this thing that we call a common ground structure, wherein we take a dynamically updated data structure to the dialogue that's got everything that we don't know, called the questions under discussion. We call it Q bank. So it's a live possibilities. So let's see, it could be the red is 10, the red is 20, the red is 30, or it could be dinner possibility is Thai, Middle Eastern, Italian, whatever it might be. We haven't decided. So anything is possible. Evidence bank is going to be evidence that someone has suggested is possibly true, and I've accepted that it's possibly true. And then we go to the fact bank, which is, yeah, we all agree that this is basically going to be the set of propositions agreed by everybody. So we're going to initialize the whole set by saying everything basically starts off as nil in the evidence and fact bank. And we create this model of questions. And we're going to basically try to add to the fact bank as we go along. And we're going to update with evidence, as I just mentioned. So here's a graphic of it. We encode the curriculum plans as propositions. So, you know, we're trying to solve the Fibonacci weight test. Propositions for questions, evidence, and facts. So I have action. This is not a language, okay? I move a red block on the right scale, which is encoded in this representation. I'm going to put a blue block on the right scale. The visual observation, this is not language, is the scale is balanced. Okay, we have an encoding of that. There's no language whatsoever. Now language says the scale is balanced, or normally it's going to say it's balanced. So, and then somebody else says, yeah. So we're basically shifting through this dialogue move from nothing known to there being some evidence to something being substantiated as a belief. So we've annotated the weights task data set with speech X, nonverbal behaviors of gesture, attention, actions, and collaborative problem solving. And then given all that, we come up with what is the common ground? What do we actually agree on? What does this triad agree on at this time? It's a very detailed annotation. The first one is gesture AMR, which we developed in the context of this work. That I'm just going to mention is basically an AMR type representation for gesture, using the syntax of abstract meaning representation. So here's a multimodal expression. Someone says, push that block left. And the gesture for push left is integrated and aligned to it. This is the gesture AMR for it, and this is the speech AMR. That's a multimodal communicative act. Okay. Now, I'm not going to talk about CPS, but it's another indicator which indicates for a group, how engaged are you? Are you moving forward? Are you having fun? Are you getting something done? We use that as another metadata clue. It essentially helps with for learning scientists constructing shared knowledge within the space. Another annotation scheme we use is nonverbal communication called the NICE framework, which basically works really nicely with our annotation of gaze and gesture and actions. And it's something that is definitely been very helpful for annotation. Actions we annotate in a very simple way using a kind of a first order representation taken from VoxML, our language for simulations for affordances. And it's very straightforward. It's something that can translate into a JSON representation as when we input it into an LLM. So the common ground annotation is important. It's basically dialogue movements. So you make a statement, you say accept, you doubt something, you question, you answer. These are all basically kind of from the ISO dialogue act or dialogue AMR. Okay, it's the same type of representations. Now, I want to introduce something called dense paraphrasing, which is going to be a way of enriching. It's a data augmentation and enrichment of utterances. So you make an expression more semantically contentful by essentially filling in all the semantic gaps. So the dense paraphrase for an expression is going to be consistent. It's going to eliminate any contextual ambiguity, and it's going to fully enrich what's not present in the current utterance. Here's an example. The utterance that's in the dialogue says it weighs 10 grams. The situated grounding for coreference essentially is to replace it with its designate, the referent. The red block weighs 10 grams. A gesture is literally just the syntax of pointing left like that, but you want to get to the actual referent by extending the distance to the end of the vector, which is going to be the yellow block. Other things involve epistemic enrichment, such as if somebody says it weighs 10 grams, then the speaker actually thinks that. So this is essentially a typical pragmatic view on framing from the epistemics. I usually believe what I say. Similarly, if you act on something, you believe what you're doing. So there's epistemic aspects to both speech acts and ontic actions that need to be accounted for. That's part of dense paraphrasing. So without the details, there's syntactic consequences for this type of data augmentation that we leverage by taking the JSON output of that and putting it in as input in context learning to an LLM. Similarly with this. Now, we have the annotation visualization. We've done the training data. Now let's see how this fits into our neural symbolic system. We're going to look at the common ground tracking, the first experiment. So we have basically this pipeline, and we're going to basically model common ground tracking by having a move classifier, which is a multimodal LSTM, a propositional extractor, which is going to basically consult a dictionary or extract content through vector similarity methods, creating a PERT embedding, and a set of closure rules, which is basically going to give us the closure of the content of a specific bank by essentially saying something, if you see it, then you believe it. Or if I have some rule that I can apply transitivity over it. We use DSC for matching the propositions with ground truth. The features we're going to be using are speech, prosody, these collaborative problem solving features, gesture encoded as k-hot vectors, and action also as k-hots. These are all going to be fed into an LSTM for basically seeing where we are. So the results are suggestive without going into the details per group. I will basically go straight away to the results here and look at, on the left, we see what's going on over time, the propositional extraction, that is how close we're getting to basically having a common ground where the fact bank is fuller than it was before, and essentially characterizing that the multimodal common ground method is actually performing substantially better than anything which is a unimodal linguistic expression, and even better than the enriched contextualized form called the dense paraphrasing form. So multimodal information is adding information to epistemic content. And this is really kind of surprising and very exciting. We took that result and tried to go a little further by saying, well, what if we actually take all the other modalities and not just look at the some kind of k-hot vector for vision or gesture, but actually turn it into a linguistic expression. So translate it into a sentence. And that's the notion of multimodal paraphrasing. So we did over the same data set. We have a component for each modality. Here's the kind of architecture. We have neural nets for each of the modality parsing or the recognition, and it comes out in whatever form we get it. We do a dense paraphrase, essentially then creating a linguistic expression that now we have a choice. We have something which we can graphically enhance and embed and put into an RNN, or we can simply concatenate and put into an LLM. And I'll talk about the latter form, because that's what we did. We did experiments with GPT-3, 5, 3.5, and 4 in context learning, where we put in the prompt of what we're trying to do. We have it basically create a multimodal machine readable paraphrase, giving us this kind of JSON output from that. Then we post that from all the different modalities to the LLM to have it come up with a human readable paraphrase, and then answer a question in a classic kind of LLM QA downstream task to see whether or not it is correct or not correct with answering a question about the current common ground. So for speech, it's basically you can do some decontextualization, kind of like we did with the previous experiment. Actions, again, these basically are in this kind of JSON output that we will then convert to sentences. And the multimodal alignment, we align the actions and gestures, and we convert all those MRPs, we put those into an LLM to create these HRPs, human readable paraphrases. Here's an example. We have this tuple of an utterance and this action and a gesture, and we have an HRP. That's my time. Do I have time left?
Yeah, you have to.
Oh, some time? Okay, great. And the HRP for that is essentially going to be this human readable paraphrase describing linguistically what the situation is that I just described. And the results show, I'll just go quickly here, that we matched the baseline from the previous experiment that we did on common ground tracking here with just using the language model without any kind of contextualization, showing that the language model does bring a lot of information that you don't get just with kind of your own LSTM with additional types of features. But with decontextualization, you get an incredible improvement. And then with multimodal decontextualization, you get a slight improvement. We don't have enough data to really validate how good it is. But this essentially shows that, I'll just go quickly, that the multimodal decontextualization, basically bringing all the different forms into linguistic expressions, really does help interpret what's going on, taking out part of those latent or hidden variables from the context, in part. So let me just give you an example of how this works. Oh, by the way, we compared this to multimodal vision language models, and it did worse, actually, probably because the sampling wasn't high enough. We only did 5 frames, and 5 frames per utterance. And that probably was no better than our actual dense paraphrases on the sub-event representations. So what you really want is to get a much higher density throughput in order to really test and validate whether vision language models are going to be an improvement. I would certainly expect that they would be. So here's the idea: reading the room. This is just what we're calling it. You have a multimodal dialogue. You're integrating this evidence from diverse modalities DP will allow you to make explicit representations of neural outputs, making implicit or contextual information explicit. And we have the neural outputs are specific to each individual modality. I will dense paraphrase each modality. So for example, from the vision and speech and gesture, I will have specific linguistic dense paraphrases for these. They can have their own embeddings. They can have their own inputs to an LLM with whatever attentional structures they have in the model. We're going to combine these just by concatenation for now. We assume we let the LLM take care of the weighted combination and the contextual prioritization. You can do that by hand. And that's what we essentially did with the first model for the CGT. And the final unified representation is something like this. And that integrates all the modalities. So here's one example, and I'll be done in 1.5 minutes. This is essentially how it works in our experiment. So we start off essentially with attention. We have an annotation. We have co-attention, which is also an annotation in this AMR-like representation. Everything is AMR, hence we call it XAMR. Speech act also will be turned into an AMR. Gesture, gesture AMR. Posture, posture AMR. And let me just give you one example that I kind of want to show. We just did an experiment on. This is the Sally Ann. There's no sound. So he's putting the block into this box. These are our gaze and action. We have gaze, action, objects. Continuing to gaze. From this, we dynamically read the epistemic state. Seeing is believing. Okay, we just take that, right? It's veridical perception. Okay, then is moving the block to the canister. Jordan, the other person, is not privy to that because he's not seeing it. So we're actually experimenting and doing the situational updating. He's absent. Okay, and of course, we're going to see him be surprised. And in the last 15 seconds, I'll just conclude with the sliding door example. So the sliding door example, we're going to have the false belief subverted. So that was a false belief. We have the way of representing that, and also then encoding it in a modal representation, which has a JSON representation, which then can be encoded into an LLM vectorized representation. Okay, so he's not looking. So we saw so he knows it's there because he subverted the false belief. Okay, let me just conclude. So in conclusion, situated constructional meaning is more than just object reference and behavior. It's this epistemic and content updating which we have to model. We absolutely need that in our models. And it can be achieved in part by adopting neurosymbolic architectures. There are much richer architectures that we haven't even talked about here, which would be holographic and hyperbolic embeddings. And it's basically, it leverages, it takes advantage of the natural NN classifiers that we have for these types of data and the LLM prompt-based reasoning that we're using. And then any type of symbolic processing that we want. So the reading the room strategy converts these different modalities into this unimodal expression that, at least for now, seems to be a fairly robust way of perhaps proceeding with some of these hidden variables that Nikhil was talking about. All right, that's it for me. Thank you. So, I'm up here, there.
Okay, thank you. We have less time than we were hoping for discussion, but we do have a few takeaways. And I do also want to mention, if you have to run at right at 5:30, I'll say right off the bat that we would like to invite you to continue the discussion with us. I think that we are going to go grab a bite at a restaurant that was recommended to us called Solar. It's a Persian restaurant that's about 14 minutes or so walking away. So if you want to come and have a bite with us and talk with us before we go to the welcome reception this evening, then that would be a great way to also continue the discussion. So, okay, but now takeaways. I think one of the big takeaways that you'll see echoed throughout to some extent is that there's a need for additional data, resources, and evaluation in physically situated, socially interactive language use between people and agents. But in my own experience, there's many challenges to collecting this kind of data. It's difficult to set up the kind of situation where someone would speak naturally to an agent. And also part of this is because when we enter into a conversation, James told us about common ground and its importance. When we enter into a conversation with an agent, there's no presupposition of what that agent knows and what they can do. So we need to find creative ways to set up this process so that people can begin to communicate with agents. We can have data that shows us how they would communicate with agents, because it's going to be different from how they communicate with people. And then we can begin this important process of data collection.
So I think in terms of takeaways for my part, we were looking at what it is that LLMs can and can't do. And I think we started with this, I think, important notion that it's not just memory retrieval, because I think it's important to address what they can do before we can pinpoint what they can't do and why that's important to work on. So to dismiss them as, memory retrieval would be kind of unfair to what they can do and also counterproductive. So we talked about that, but then we focused in on this notion of reasoning and why it is that they're not reasoning, and instead provided this alternative explanation, which is that they're extrapolating from pre-training data, which carries into what Nikhil talked about and also what James talked about in terms of what can be done with this information. And really, I think the most exciting part of this is the fact that we now have a huge amount of work to be done, right? So this doesn't mean that LLMs end research. It just means that they make all of the things that we've been doing for quite some time even more exciting, and in the ways that have been described by Nikhil and James.
So we can see that the sophistication of language models now actually allows us to ask some really interesting questions about how they do and don't correlate with what we understand about human behavior. We also can see that in these results, which can be empirically validated, we can motivate why some of the shortcomings of LLMs are actually downstream of decisions that we have made in order to make training tractable. And so this allows us to isolate those hidden variables that the LLM doesn't have access to. And now we can start to imagine how we might build superstructures around models, make them access this type of information, and also imagine alternate training paradigms that would allow us to circumvent some of these shortcomings.
As I just said, unimodal representations seem to be promising, but they're not going to solve anything by any means. We need more data. But as I say here, and as Claire and the others said as well, more data to solve everything. We need to do alignment, and alignment to the intents and beliefs of the agents, which is not so clear. Those are the things that are being spoken. And we need to also have new training paradigms and evaluation paradigms. So we were hoping that we could have perhaps some discussion about evaluation too, which we really haven't talked about except on experiment by experiment basis. But I think the idea of taking LLMs in their current guise and throwing them into multimodal problems and context is a little unfair. And we need to have enough data to actually see whether it's even useful, but we need to actually create new evaluation strategies. And I think that's one of the things that we've been trying to do. I'm kind of hopeful and excited that the information, which is basically semantic memory in an LLM, could perhaps help eventually leverage what is episodic and instant and experiential in our everyday experiences. So we'll see how that goes. As Harish just said, it's actually an exciting sort of beginning, and there's really nothing finished yet.
Okay, should we take questions? Yeah. Questions? Or anything, if it's not a question and you just want to add something or comment, yeah.
Unless there's something in the document, if someone's added something.
There are quite a few, but none of them are on the side. Is there anything else that maybe watched others' talks. Any other threads that you saw or want to relate?
I mean, there's a bunch of stuff
Yeah.
that there's no time to go into. I think there's my takeaway at this point is basically that LLMs maybe leave more questions unanswered than they've answered, which is actually rather exciting because it means that there's more research to do. And just the space of possible questions that can be asked is actually broader now, and that's really interesting, and I think it's an exciting place to be.
I have a question for you. I wanted to talk about.
Yeah.
So why don't you use the largest models?
Okay, yeah, we can talk about this earlier. Yeah, so I think this is a question we probably all heard, you know, in your reviews that you get back. Why did you evaluate on O3 or whatever model came out last week? And I think there are some strong reasons to not solely test on the biggest closed source models, and that primarily deals with the fact that you can't really access the internal state of something like GPT-4. And that provides some severe limitations on what you can do with respect to answering falsifiable questions, because you can always push back and say, why, you know, how do you know that that scale is not going to solve this? And I would counter that if you can't show me what a non-performant answer would look like, then I don't think it's really useful trying to ask that question unless you can actually examine what the model is doing. So I think, you know, GPT-4 and all these models are great. They're out there. They're available, but they put some severe limitations on the types of questions that you can ask and answer scientifically. And it becomes really hard to conduct kind of Popperian science using a proprietary model.
Two-part question. Your thoughts on agentic workflows that are being built, and the other one is it a good idea to fine-tune a very large model or join fine-tune multiple smaller modules focusing on each and every specific aspect of your multi-model problem?
Okay. Yeah. So I assume that by agentic workflows, you effectively mean an LLM that decides, you know, what tool to access to do something. Leaving aside the issues I have with the term agent used in that way, I think there's some interesting applications, but we run into some questions about how validatable those interactions can be, because ultimately you're handing off information from one system to another, and especially this kind of comes back to the closed model. We don't really know what the model is handing off. We don't know how the transfer protocol is maybe affecting that information. And so there's a bunch of questions in there about how reliable that transfer information is. And so it's an interesting area of research. It also opens up some questions about how can we be, you know, provide guarantees on the model behavior when it's hooked up to this external system.
That remains the same even if it's a single model.
Sure, yes, yeah. But if we're you know, I assume you're talking about things like, you know, I want to book a flight or a trip, but I have GPT-4 Planet also do the reservations for me or something. So it's handing off information, performing instructions on an external system. And that necessarily comes with some question about how that information is robust or fidelity, you know, as you hand it off to the system. And then with respect to the other question, firstly, I'll let them just speak, but I think it really depends on the use case. Because sometimes you may find that the bigger model is, you know, you can just fine tune it on your task and it works perfectly well for that task. Other times you may find that the distribution of data that you're dealing with is diverse and enough that you may just want to handle, you know, hand off individual pieces to smaller models. So it's a really difficult question, I think, for me to answer without going really deep into what the specifics of the problem I'm trying to attack are.
Maybe something debatable. So since I work in NLP and robotics, there's a need for having small models on board robots. So to some extent, there's a push to figure out how we can fine-tune models that will fit onto a robot. But there's kind of a counterforce in the research where you'll see some people who are doing that kind of fine-tuning and working with smaller models, because right now, it's not tractable to put a large language model on board a robot. It simply isn't. But we also see a lot of research that's just forging ahead with the large language models under the assumption that eventually we will be able to make those models fast enough and small enough that we will be able to fit them on board the robot, that the technology will come. So to some extent, I think that the answer to that question could also be how much faith you have in that actually changing to the point where one of the large language models would work for your application.
Maybe I think just to add to this whole scaling loss and what that would mean to a smaller model, I think there's three important elements that determine what a model can do. One is the number of parameters in terms of scale. And the second is how much data we train on. But there seems to be a third element, which is the actual quality of the data that we use for pre-training. And so if you see Llama 3.2, for example, it's a 1 billion parameter model, which is, I'm going to call it interesting. It can do interesting things. Whereas typically you would need a much larger model to do similarly interesting things. So there seems to be a combination of distillation and data quality or refinement of data quality, which can lead to slightly smaller models still doing something that's useful. And of course, there's Moore's law and all of that, and eventually you're going to have GPUs becoming cheaper and so on. So it would happen, but I think the underlying message that we were trying to get at might have been, and I don't know, I may be wrong, is that there are some inherent limitations to what all of these systems can do. And making that an agent is not fundamentally changing what it is that the model itself can do. There's something missing, and maybe it's this grounding that's what's missing. And maybe that is something that needs to be addressed differently as opposed to through scaling. In my head, again, I may be wrong, scaling and agentic kind of behavior is not going to address this fundamental limitation. Maybe something else would.
Just finally, follow on what you just said, as well. I think the data quality is really a huge issue, and that would perhaps enable much smaller models when put together with, say, augmented systems such as RAG. And I think that's a really exciting area to explore. That interestingly brings up this role of lexical and language resources, because that's exactly what they're for. Therefore, creating better data. And so I think the next phase, I think, will be a decided, very conscious integration of not necessarily the classic good old-fashioned lexical resources and language resources, but definitely the appropriate integration of them into how LLMs can be made smarter and smaller and integrated to things like that.
Any other thoughts, questions?
So I found this very exciting. One of the things I found exciting in your part, James, was that you really have multi-agent scenarios here, right? And you just sort of touched on the issue of alignment kind of at the end. So there was a fairly influential theory of alignment about, I think 25 years ago, by, I think his name was Garrett, and he had a kind of collaborator out of Glasgow, I think. And I think one of the titles of their paper or his book was Alignment in Communication, right? So is that something you're drawing on here as well?
Absolutely.
Or yeah?
Yeah. So already in the common ground tracking paper that Nikhil and I worked on, and Nikhil can speak to this, we had alignment. The aligning of these different modalities and the information came from, right now, a very coarse grained and somewhat intuitive of overlap of the interval, but that certainly is not at all sufficient, according to the Garrett model, for example. But it's a start, and it also pinpoints exactly what we're missing with that, so we can draw on those resources again. We'll say more about that.
Yeah, so I think in the field, kind of derisively think of the Star ACL conferences, right? Alignment is something that came about in the last 2 years, but in reality, alignment has been a topic of literature in this field and other related fields for many years. And so the alignment of intents, the alignment of goals, the alignment of assumptions, right? All of these things are in some sense predicated upon how we use terms in context. But the language model, as we currently understand them, is kind of hit or miss with keeping track of those. In large part, I think mostly because the information is not made available during the training. And so the human agent, the human AI kind of collaborative process, I think really needs to take a more robust view of what alignment means. It's not just about, you know, what is the safest or most desired output given the context. It also has to understand what's the long-term goal of engaging in this interaction with the AI in the first place, right? We're doing this because we want to get something out of it. And a good collaborator, AI, is going to have be attuned to that at some level.
Yeah, I think maybe a short follow-up on this. I mean, there was also all this work on discourse, right, by Kenny Seidner and Barbara Rules, and they also have these notions of intentional and attentional states and a lot of this work has sort of, I don't want to say been forgotten, but just sort of put on the shelf a little bit. But now might be the time in this sort of new representational space to kind of take a look at that again.
Yeah. So Katie Seidner, you may or may not know this, youngsters in the group, but you have Bonnie Weber and Mark Gross and Katie Seidner and many others, all the way to people like David Trown and Brad Goodman and other people. This idea of a dialogue, a notion of borrowing on some of the Prague schools of information structures, of given new and what is the focus, what's the topic, and then the dialogue as it proceeds, the informativity. These are all incredibly important notions that we are actually starting to incorporate. Candy Seidner is just coming on as an advisor on our NSF in the next couple of weeks. So yeah, absolutely. That doesn't mean that we have to really take it more seriously. I think the integration of such ideas is, I think, it's certainly workable within a more symbolic architecture, because you're doing symbolic representation of this. You can encode them into various types of bind bundle holographic vectors, or maybe some type of general clause embeddings if you want, or let the LLM take care of it. But definitely it's worth experimentation to see if that does improve things. Given what we've seen just with some symbolic representations, as well as adding UMR and dialogue AMR to some of our discourse, it helps. It helps enormously. Which would then again feed back into allowing you to have smaller models, because if you have that type of representation, that's what syntax was all for, right? Originally, to take care of long distance dependencies. These are long distance dependencies in discourse, and you don't necessarily need a 32K context vocabulary in order to do that. So, yeah.
And you might want to say something about this, because I think at least what I see with like the sort of older theories, what they really provide is a layer of explainability that large language models don't really do. You can say, I observed this phenomenon of the language model, and this theory provides an explanation for why it came out this way. And what we can do is, by providing these sort of symbolic explanations, you can actually feed that into the language model and sort of guide it into extrapolating from the right part of its training data, because it probably has seen some representation like this before, because it's trained over, you know, all of Candy Seidner's papers, for example. And so you can actually guide it into making robust inferences based on symbolic information. But you have to know that that's the sort of thing that you should be asking of it in the first place.
Yeah, no, absolutely. I think it's about that guiding and how we do that. And one of the things that seems to do this is, you know, explicit chain of thought prompting, which is a very rough approximation for more complex and more involved neurosymbolic mechanisms, right? And, you know, you can straight away see what's going on. Of course, it's not faithful. That's not what the model is inferring. But if it could access something that's more structured, AMR, for example, in that context, now that would make things truly powerful, because now you can fill in slots more explicitly, you can reach into different parts of the pre-training data more effectively, and you can then extrapolate based on that in a manner that is interpretable and therefore controllable, and also now more robust because it's way more controlled. And I think that is one direction that would probably be very exciting. You want to add something?
I'll just add one thing.
Yeah.
So on the note of hybrid architectures with some kind of symbolic aspect and also maybe a large language model, I'll just say that that's what we are finding most promising in our human robot dialogue work as well. And that's partially because the LLMs are still very slow and some of the symbolic architectures are quite fast. But I also just want to note that we have so many people coming into NLP because of the hype around large language models. So sometimes I find that when people come to me and they say, I have this idea for using large language models, if they're new to this world, then I might ask them to step back, think about what the hybrid architecture could be, and then think about, do you really need a large language model? For some of these cases, a base model works fine. Word embeddings work great. So I see it as our responsibility as NLP practitioners as well, moving into this cross-disciplinary world to say, maybe you don't need that much. Maybe this just adds hallucinations and complexity that you really don't need for your task. Any other thoughts, questions? Do you want the mic or?
Okay, well, can you hear me?
Yeah.
Yes, yeah. And anyway, I think this is fantastic work, and it's very much related to what I've been working as well about the grounding and roles, etc. I want to sort of ask about but also two things. One is the actual representation and sort of techniques to represent knowledge in the say robot's brain. But something like knowledge graph is nowadays very popular and very much used to represent it, and I think that might actually be a very interesting approach to see how this knowledge and common ground can be built. And the second thing I consider sort of related to that is that important thing there with building common ground is the context and how to sort of decide what is the context, how much of inferencing we are willing to do in order to understand what the partner says and integrate it in our knowledge, or how much there is to say that that's on the side.
Those are great questions. So I want to hear from James, I think, on the common ground piece as well, but I'll take a moment to answer that. I think that whether you want a knowledge graph or not depends on what kind of task you're looking at. So the kinds of tasks that I'm working on are more like disaster relief and things like that. So I think the second piece that you mentioned, knowing about the physical context, we're prioritizing that first. But there is still this question of how you represent language and how it maps to what a robot knows and can see. So right now, most of the state of the art is drifting towards scene graphs. So scene graphs give you information about relationships of like above and below, and they can also give you some information about what a certain object is. They have these semantic labels, and then they call them semantic scene graphs, which is personally offensive to me, but I'll let it slide. So I think that the trick there, or the problem that we're still running into, is that the level at which a robot is going to slice up the world is very different from what a person does. So I think that we personally, I think the key is finding better interfaces of that information in order to establish that common ground, so that you can see kind of what the robot already knows about. Because we are really good at engaging in those kinds of inferences and trying to figure out what the other person is talking about. And robots so far, not good at that. So we can do a little bit more than they need to do, but I'm still of the opinion that the burden shouldn't all be on us. We've come further than that. So I would say that our answer right now is having language to AMR and dialogue AMR, and then there's actually quite a bit of work that maps AMR to scene graphs, which is lovely. And then we usually have a hybrid architecture where for certain cases, we can pass things to an LLM instead, and then we pass off to another representation of the robot's world model. So it can make a good guess about exactly what you're talking about in order to ground any references in the language. So, but I can share a paper with you if you want to learn more about that.
Thank you.
You want to take?
Yeah, I know the way. I'll just
Okay.
So, yeah, great question. The encoding of situational context is geared to our mentor, Chuck Fillmore, who basically didn't just have frames, but he had a much richer notion of epiframes. And so frames are essentially encodings of our human everyday experience, right? And so the frame you have for dining, for example, is very abstract. So if we were to collect such data, we need to essentially we need to collect what the experiences are, not just encode from, say, a vision system to recognize this is a fast food place, this is a this is a, you know, whatever kind of bar. We need to look at the behaviors that are the interactions between clients, all the participants, and that's of course very familiar. So you encode everything you can object detect, which would be appealing to the Keel's group, but also the gaze and the gestures, and then everything we can possibly construe, partly by hand, which might be the assumptions of what am I doing here, and it's kind of a script, and then just observing. You have to observe. So today we were at some restaurant for lunch, and we found out by accident that it's actually kind of a la carte, a flat fixed, well, not a la carte, but basically a buffet. And certain things came up just by accident. So Harish had an order of a Caesar salad, and I wanted one. He was able to give me one when he brought the other one to the table. So these are very dynamic and unexpected kinds of scenarios and interactions that you have to observe in order to be able to annotate and then model. You can't possibly predict it. So after all of that, with enough data, you can start learning some things about how to differentiate the interactions and what you might expect from one establishment to another establishment. And that's a pattern of experience that we have as humans. And I know it's a vague answer, but I think it's a hard problem, right? But I think we're doing some of the right stuff. And just one last comment is I think encoding a lot of the graphical information and AMRs, the XAMRs I call it, there are a lot of very exciting unexplored techniques for how to use sparse embedding, sparse memory that has been around in actual biological neural systems for a long time that do not require 2 million epochs of training and much less data using hyperdimensional computing. So if you have hyperdimensional representations, you have orthonormal representations, you have content addressable information from using convolution and correlation bind up operations. So it's really it's a quite exciting area that was dropped when Hinton basically showed that, you know, ComNet could basically take everything, but the people like Smolensky and Plate and Pollock and others like that, mostly from Hinton's lab, they kind of dropped their work except for Penty Canerva. And Canerva's work is really the only work to kind of continue this. And Penty is brilliant, and I think we need to really explore this notion of hyperdimensional computing. So, a little plug.
Final thoughts, you know, it's getting late.
Sorry, we're sort of late here.
How about if you want to for a question, and by the way, we were told that there are drinks and very light bites at the welcome reception, but there's not like a full meal. So if you want to join us, we can gather for a moment, and then we're walking over to Solar.
And it is already almost 6. So.
Yeah.
And so we will put a video of this up on YouTube. So we'll post that on the website once it's uploaded. So check the website again in a few days, I guess.
And thank you for attending and for staying the whole time.
Hello. Yeah, I'll say LAR. That's what we're going to need. You also